Welcome, weary traveller of the modern world, as we gently unmoor ourselves from the present moment and begin a slow drift through the boundless ocean of time. Tonight, we journey not across the familiar tapestry of continents and cities, but into a version of Earth that whispers from the very edges of memory. This is not the vibrant, breathing world we inhabit, nor the one charted on maps or glimpsed by satellites. No, this is an Earth far older than whispered histories, deeper than ancient bones, preceding even the first breath of oxygen in our atmosphere. We are venturing into the Archean Eon, a dreamscape of deep time where the very ground beneath us was still sketching its first hesitant forms. Imagine a canvas of planetary creation, where the fundamental elements had yet to decide their ultimate purpose. This was a world utterly alien, devoid of animals, silent without plants, a stark landscape unfamiliar to any modern eye. The sky above wasn't a comforting blue. The air was a toxic cocktail, unfit for a single breath. The sun, a younger, dimmer star, cast its light upon shorter days. The oceans, vast and enigmatic, swirled with dissolved elements that would prove lethal to any contemporary fish. And yet this was the genesis, not the Earth's absolute beginning, but the dawn of what we can still trace, the birth of the oldest rocks, the first fragile fragments of what would one day become continents. And in that primordial soup of chemical chaos, the earliest, most tentative sparks of life itself. It's a peculiar thought, isn't it, to consider that everything we know, the simple act of breathing, the grounding sensation of walking, the nurturing of food, the building of shelter, all required a vastly different Earth, one that arrived much, much later. Yet, if we seek to comprehend our present existence, we must surrender to this ancient past. The Archean wasn't a realm of quiet simplicity, it was a cauldron of ceaseless activity, volcanic, unstable, forever reshaping its nascent form, and perhaps that tumultuous energy is precisely what makes it so profoundly captivating. It is not a peaceful bygone memory, but a long, slow, powerful conversation between raw heat, flowing water, emerging rock, and the relentless march of time. So wherever you find yourself listening, at whatever hour the cosmic clock marks, be it the fading light of evening, the hushed promise of early morning, or somewhere in the gentle in-between, take a moment to truly settle. Let your thoughts unfurl, like ancient scrolls unrolling into an infinite expanse. We are not rushing through this epic tale. Instead, we shall allow it to unfold at the Earth's own majestic pace. Slow, steady, and filled with the profound surprises of creation. The Archean is more than just a forgotten chapter in our planet's immense story. It is the very first part we can still decipher, a foundational text etched in stone and memory. And so, let us begin our gentle descent into a time before trees, before breathable air, before even the very word Earth held any familiar meaning. As the Archean Eon dawned, our nascent Earth was in a profound state of recovery, not from the fleeting impacts of civilization or the shifting currents of climate change as we understand them today, but from the raw, unbridled violence of its own tumultuous birth. The planet, a mere few 100 million years prior, had coalesced from the swirling dust and rocky debris orbiting our youthful sun. It had already endured at least one colossal impact, the cosmic ballet that birthed our moon, leaving indelible scars that still profoundly influenced its surface and inner architecture. The immense heat generated by these ancient collisions, coupled with the relentless energy released from radioactive decay deep within its core, caused the early Earth to glow, a fiery ember from its very heart. By the time the Archean truly began, approximately 4 billion years ago, a delicate cooling process had commenced, though it was merely a whisper of the stability to come. The planetary crust had started its slow solidification, yet it bore little resemblance to the thick, steadfast surface we recognize today. Instead, it was a restless, fragmented shell, thin and brittle in countless places, constantly rupturing and cyclically melting back into the churning, molten interior. Volcanoes were not isolated features dotting the landscape. They were ubiquitous, an ever-present force. Entire regions groaned under the dominion of volcanic activity, with molten magma ceaselessly ascending from the depths, relentlessly reshaping the emerging surface again and again. Above this profoundly unstable crust hung an atmosphere that would have been instantly lethal to any life form familiar to us. It was likely a dense, sweltering blanket, saturated with gases such as carbon dioxide, methane, ammonia, and vast quantities of water vapor. Oxygen, the very essence of the breath you draw now, was almost completely absent. Had you by some impossible feat stood upon that ancient surface, your gaze would have been met with little beyond towering thick clouds, perhaps occasionally revealing the stark silhouettes of volcanic islands rising from immense, dark oceans. You would not have survived more than a few fleeting breaths, if that, not because the planet was barren or lifeless, but because it was merely taking its first fiery steps towards existence. The oceans, those vast liquid cradles, were already in place by the early Archean, though their precise genesis remains a subject of cosmic debate. Some celestial theories propose that this primordial water arrived aboard icy comets, myriad bombardments during the planet's infancy. Others suggest the water was an intrinsic part of Earth's original composition, trapped within minerals deep within its interior and gradually released over eons through the persistent breath of volcanic outgassing. However it arrived, these oceans were fundamental to the unfolding story. They veiled the majority of the planetary surface, interrupted only by scattered volcanic landforms or nascent fragments of the earliest crust, and these were not the inviting, clear blue waters we envision. Without oxygen, iron dissolved freely, painting the seas with a darker, perhaps greenish or reddish hue. Coupled with the hazy atmosphere and a dimmer sun, the world would have presented an utterly alien visage, muted, heavier and profoundly volatile. Despite this seeming harshness, this was a world pregnant with chemical potential. The intricate dance of heat, minerals, gases, and water created an almost infinite tapestry of opportunities for molecules to collide, to react, and to subtly evolve. Somewhere within this primordial mix, the miracle of life began. We may never know the exact moment or the precise mechanism. The intricate details remain shrouded in cosmic mystery, perhaps forever beyond our full grasp. Yet, by the middle of the Archean, approximately 3.5 billion years ago, the faint, indelible evidence suggests that life had already taken root, not as plants or animals, not even as complex cells, but as microbial organisms, single-celled entities, remarkably simple yet possessing the fundamental capacities for growth, reproduction, and metabolism. They flourished within the oceans, most likely in shallow, sun-warmed environments rich with minerals and diverse energy sources. Some clung tenaciously to nascent rocks, others drifted freely within the currents, while many congregated around the mesmerizing hydrothermal vents, where superheated, mineral-laden water surged from fissures in the deep seafloor. The very earliest forms of life might not have depended on sunlight at all, choosing instead to harness chemical energy from the earth itself, a process known as chemosynthesis. These hardy organisms harvested their vital energy by breaking down hydrogen sulfide, methane, or other compounds perpetually issuing forth near these underwater oases. Even today, echoes of these ancient ecosystems persist at the bottom of our modern oceans, home to life forms that require no light to survive, only the intricate alchemy of chemistry and the patient hand of time. Eventually, a truly remarkable transformation unfolded. Some of these pioneering microbes discovered an ingenious method to utilize sunlight, even beneath the dim, hazy skies of the early Earth. This process, photosynthesis, embarked on its long journey to fundamentally reshape the entire planet. Initially, it did not produce oxygen. Earlier forms of photosynthesis likely consumed hydrogen or sulfur compounds as their electron donors. But with the slow march of eons, a new revolutionary form emerged: oxygenic photosynthesis, performed by resilient organisms known as cyanobacteria. These microscopic architects were the first to release oxygen as a byproduct of their solar energy capture. They did so gradually, almost imperceptibly at first, and the nascent oxygen did not immediately accumulate in the atmosphere. Instead, it reacted voraciously with the dissolved iron in the oceans, forming rust-like minerals that gracefully sank to the seafloor. These iron-rich layers eventually solidified into the majestic banded iron formations, geological evidence, still visible today, that oxygen was slowly, irrevocably beginning to alter the very chemistry of our planet. Meanwhile, on the nascent surface, the first fragments of what would eventually become continents were embarking on their slow, uneven formation. Instead of vast, cohesive land masses, the crust presented itself as a mosaic of small pieces, often termed protocontinents, scattered like an unfinished cosmic puzzle, not yet ready to be assembled. These fragments coalesced from repeated cycles of intense volcanic activity, subsequent cooling, and the relentless churning of the crust. As they collided and gradually fused, they began a slow growth into more stable blocks. The ancient cores of today's continents, known as cratons, are among the oldest, most resilient parts of Earth's crust, many tracing their origins back to the Archean. You can still seek them out today in places like the Canadian Shield, the heartlands of Australia, the rugged landscapes of South Africa, and parts of the serene Scandinavian regions. These geological anchors are remarkably stable, having patiently endured billions of years of tectonic forces, relentless erosion, and profound metamorphism. When geologists study these cratons, they are gazing directly into Earth's deep past, at the very surfaces that once floated in the strange dark Archean seas. The movement of these early crustal fragments might have prefigured the earliest forms of plate tectonics, though the precise details remain a vibrant topic of ongoing research and cosmic debate. Modern plate tectonics, with its rigid plates gracefully gliding over a viscous mantle, may not have been fully established. The Archean Earth was a hotter realm, which could have rendered its crust more pliable, making the boundaries between these nascent plates less defined, more fluid, yet tantalizing evidence of subduction, where one plate plunges beneath another, of collisions and of crustal recycling hints at a dynamic, ever-evolving planetary surface. Interwoven with these grand geological shifts, the very length of a day on Archean Earth was markedly shorter than our familiar 24 hours, perhaps a fleeting 14 to 16 hours. This accelerated spin was a lingering echo of the planet's initial momentum after its violent formation. Over eons, the moon's persistent gravitational embrace generated tidal forces that gradually, imperceptibly, applied a brake to Earth's rotation. But during the Archean, the world turned more swiftly, and these shorter days profoundly influenced everything, from embryonic weather patterns to the powerful rhythm of the tides. The moon itself, freshly formed and still in its slow retreat from Earth, would have dominated the Archean sky, appearing significantly larger, a luminous, watchful eye. Its gravitational influence was far more potent, pulling at the burgeoning oceans and contributing to tides of immense power. These ancient tides, in turn, may have acted as a cosmic mixer, churning the oceans, driving chemical reactions, and providing a dynamic stage for the development of early life. They also likely played a crucial role in the patterns of erosion and sedimentation along the nascent shorelines of the Archean seas. A planetary magnetic field, a silent, invisible guardian, was also firmly established by this time, generated by the swirling motion of molten iron within Earth's outer core. This magnetic field, even in its early, perhaps more erratic state, shielded the young planet from the relentless onslaught of solar radiation. One might wonder if it played a crucial, perhaps even foundational role in preserving the nascent atmosphere and protecting the fragile stirrings of life from harmful cosmic particles. While not as robust or stable as its modern counterpart, it existed, another quiet, profound step in the planet's long, arduous journey towards habitability. One profound absence you would have noted on this early Earth was that of noise, not in the symphony of sounds we perceive today. There were no birdsong, no buzzing insects, no rustling leaves, no animal calls. The world was utterly quiet in a way that is now almost impossible to conceive. The sounds that did exist were purely geological, the thunderous roar of volcanic eruptions, the relentless crash of ocean waves, the occasional deep groan of a cracking crust. But no biological sound. Life had not yet learned to sing, to chirp, to breathe audibly. That symphony would emerge much, much later. The Archean climate was a tapestry of variability, influenced not only by the fainter young sun, but also by the fluctuating levels of greenhouse gases. With little exposed land to shape atmospheric circulation and no complex ecosystems yet regulating the carbon cycle, temperature swings may have been more extreme, both locally and globally. Glimmers of evidence suggest periods of intense heat, yet other signs hint that parts of the Earth may have experienced cooler climates, perhaps even limited glaciation. The delicate balance between the persistent outgassing from volcanoes and the slow process of chemical weathering played a pivotal role in modulating this nascent climate. As for the surface itself, it was utterly barren. No plants anchored the soil, no roots fractured the rocks, No organic material accumulated over time. The landscapes were sculpted entirely by the raw forces of wind, water, heat, and the relentless grinding of tectonics. Rain would fall, carving ephemeral rivers and streams, but with nothing to impede erosion. Sediments moved swiftly, depositing in layers that would eventually harden into rock. These earliest sedimentary rocks, when they miraculously survived, recorded the stark outlines of an empty world, the quiet, ceaseless movement of water, and the slow, patient accumulation of material on the seafloor. And yet, even within that profound silence, the Earth was inexorably moving forward. Every volcanic eruption, every subtle chemical reaction within a tide pool, every nascent microbial lineage marked a step in a grand unfolding process that would eventually culminate in everything we know, the very air we breathe, the stable continents we inhabit, the intricate ecosystems upon which we depend. The Archean was not a mere footnote in history. It was the planet's first sustained act of transformation, meticulously setting the stage for the vibrant world that was to come. We need not rush past it. There is still so much to uncover in those ancient oceans, in the first hesitant raindrops, in the primordial conversation between rock and water. The crust was slowly growing, the seas were shifting their chemical composition, and life, however minute, had made its grand entrance. Just ahead, the world would begin to change in ways that could no longer be reversed. The quiet beginnings of the Archean were starting to echo, and from here we can continue to follow where those echoes lead. By the time the earliest microbial life began to tentatively find its footing in the Archean oceans, the world above the surface remained utterly inhospitable, a realm of profound contrast. The atmosphere of Archean Earth was a thick, alien shroud, completely unbreathable by any modern standard. There was no oxygen to speak of, not freely in the air, not dissolved in the water, not even locked away in minerals near the surface. It was a planet without a breath, at least not one that we in our oxygen-rich existence would ever recognize. The dominant gases were primarily carbon dioxide, methane, and nitrogen, with smaller yet significant quantities of ammonia, hydrogen, water vapor, and perhaps sulfur-based compounds belched forth by constant volcanic activity. These gases originated not from the delicate processes of biology, but from the raw, unbridled forces of geology, released through ceaseless volcanic eruptions, persistent outgassing from the mantle, and the fundamental chemical reactions occurring at the surface. Earth's early mantle was a hotter, more chemically active cauldron, far more prone to releasing these volatile compounds. This ongoing, profound exchange between the planet's churning interior and its nascent atmosphere was one of the primary architects of the early climate. The atmosphere itself was considerably denser than today's delicate veil. While no precise measurement exists for the surface pressure of that ancient epoch, models suggest it may have been several times higher than current levels. This immense concentration of carbon dioxide would have created a powerful greenhouse effect, a crucial necessity, given that the young sun was still significantly dimmer. Without that insulating layer of gases, Earth's surface would have remained a perpetual sphere of frozen ice. Instead, the thick atmosphere managed to trap enough heat to keep the oceans liquid and the surface temperatures above freezing. Yet, this was far from a comfortable equilibrium. Surface temperatures were likely higher than today's global average, though probably tempered from the searing extremes of the preceding Hadean period. Local conditions would have varied wildly, a mosaic influenced by intense volcanic activity, swirling ocean circulation, and persistent cloud cover. The sky itself may have been painted with a different hue, perhaps an orange or reddish tint, owing to the scattering effects of the dense, dust-laden atmosphere and the complete absence of an ozone layer to filter sunlight. Ultraviolet radiation from the sun would have bathed the surface with far greater intensity than it does now. Without an ozone layer, which today forms through the intricate dance between oxygen and UV light, there was nothing to block the more damaging, high-energy portions of the solar spectrum. Any nascent life that managed to exist would have required profound protection, either by dwelling deep underwater, finding refuge in the hidden crevices of minerals, or evolving robust resistance to UV exposure through ingenious chemical means. This is one compelling reason why deep-sea hydrothermal vents and shallow marine sediments are often considered plausible cradles for early biology. They offered both chemical energy and vital physical shelter, at a time when the surface was still a dangerous, unforgiving realm. the profound absence of oxygen also implied a world without oxidative weathering on land. There were no rust-colored soils, no oxidized minerals, and none of the complex geochemical processes that define our modern carbon and oxygen cycles. The chemical reactions that shape the land and water were fundamentally different, operating under a primordial logic. Iron, for instance, remained freely dissolved in the oceans, imparting a distinct color to the water and fueling a global process that would eventually produce the majestic layered iron deposits, the banded iron formations. Once oxygen began to accumulate in the merest trace amounts, this slow, persistent interaction between the atmosphere, oceans, and crust began the meticulous groundwork for future transformation. Microbial life, particularly the earliest photosynthetic organisms, would, molecule by molecule, begin to subtly alter the chemistry of their surrounding environment. Even before oxygen became a dominant component of the atmosphere, life was already influencing the delicate balance of gases, cycling carbon, producing methane, and participating in reactions that gently reshape the world around it. Methane, a gas often shrouded in mystery, played a particularly intriguing role. Produced by early microbes known as methanogens, this gas is a far more potent greenhouse agent than carbon dioxide. In an Archean world with limited oxygen and abundant carbon sources, methane likely accumulated in significant quantities, powerfully reinforcing the planet's ability to retain crucial heat. There's even a fascinating speculation that methane haze, formed when methane concentrations became sufficiently high, could have profoundly affected the climate and the very appearance of the sky, much like the enigmatic moon Titan, Saturn's largest satellite, appears through its thick atmosphere today. Such hazes, by reflecting incoming sunlight, could have paradoxically cooled the planet, counteracting the warming effect of other greenhouse gases. This dynamic interplay between warming gases and cooling haze, in a constant delicate tension, may have created periods of profound climate instability, sudden shifts from warmer to cooler conditions, and back again. These early feedback loops were primitive versions of the complex climate regulation systems that would slowly, intricately evolve over billions of years, ultimately leading to the relative stability of the modern Earth. Despite its inherent volatility, this Archean atmosphere was not chaotic in the sense of constant, unpredictable change. It possessed a profound stability over immense geological timescales. It had its own intrinsic patterns, cycles, and chemical pathways, simply not the ones we are familiar with. It lacked oxygen, yes, but it operated under its own internal logic, driven by the deep forces of geology, by the persistent heat of the planet's interior, by the relentless pulse of solar radiation, and eventually, subtly, by the burgeoning power of biology. The air, as it existed then, formed a self-sustaining system that supported the planet's unique chemistry and buffered its temperature, even if it could not sustain the breathing of animals or the growth of plants. We often tend to perceive oxygen as the quintessential gas for life. Yet for the first half of Earth's sprawling history, it was either entirely absent or, paradoxically, a profound threat. Oxygen is inherently highly reactive. In a world utterly devoid of it, life evolved along entirely different metabolic pathways, utilizing sulfur, nitrogen, or iron as electron donors and acceptors in its intricate processes. When oxygen finally began to make its appearance, even in minute quantities, it would have been acutely toxic to many of the organisms that had meticulously adapted to an anoxic environment. What eventually became our lifeblood began its journey as a potent pollutant. This profound chemical shift did not occur instantaneously. For the vast majority of the Archean, oxygen produced by photosynthetic microbes did not reach the atmosphere in significant quantities. It was voraciously absorbed by dissolved iron in the oceans, by reduced minerals on land, or simply broken down by eager reactions with volcanic gases. Earth possessed a colossal oxygen sink, a gargantuan chemical sponge, ceaselessly soaking up the newly produced molecule before it could ever accumulate in the air. It was not until these immense sinks began to slowly saturate late in the Archean and well into the Proterozoic Eon that oxygen started its gradual ascent into the atmosphere, leading to the monumental event now known as the Great Oxidation Event. But that transformative epoch was still far, far ahead. For the time being, the Archean atmosphere remained thick, heavy, and utterly alien. It was more than just a blanket of gases. It was a vast, intricate chemical machine, one that exchanged energy, filtered radiation, and sustained the first delicate ecosystems, even if indirectly. It did not resemble ours, it did not function like ours, but it worked. And perhaps more importantly, it left behind tantalizing clues, traces of that ancient atmosphere surviving in the deepest rocks, in minuscule bubbles, trapped within minerals, in the precise isotopic ratios found in sedimentary layers, and in the unique chemical signatures of microbial metabolism. All of these whisper tales of what the air was composed of and how it slowly transformed over the immense canvas of time. We cannot journey back to directly sample the Archean atmosphere, but through the patient art of geochemistry, we can meticulously reconstruct fragments of it, enough to piece together a compelling picture, if not a perfect snapshot. Some of the most crucial evidence emanates from sulfur isotopes. In the profound absence of oxygen, sulfur undergoes specific reactions that leave a distinct, indelible isotopic fingerprint. These unique signals manifest in Archean rocks, but gracefully vanish after oxygen levels begin their rise, making them a reliable marker of ancient atmospheric conditions. When we meticulously study rocks from different epochs and locations within the Archean, we can observe how the delicate balance of gases shifted, how localized changes unfolded, and how the planet slowly but inexorably moved towards a new kind of atmosphere. It is all too easy to overlook the profound importance of a planet's air. We breathe it constantly, yet rarely pause to contemplate its genesis or its long, winding evolutionary journey. Yet, in the Archean, the atmosphere was not merely a passive environment. It was an active, potent participant in Earth's grand transformation. It meticulously controlled the temperature. It dictated the very chemistry of the ocean. It meticulously set the stage for which life forms could possibly exist, and how, without oxygen, there were profound limits. Large, complex life was simply an impossibility. But even within those profound limits, the early Earth discovered a way to persevere, to move forward. The atmosphere, strange as it was, provided the fundamental conditions for life to persist, to replicate, to innovate, and eventually to reshape the very air itself. It was a planet learning how to breathe, not with lungs or leaves, but with the intricate alchemy of chemistry and the boundless patience of time. And as the oceans began to subtly reflect those changes, as new layers of rock started to record the first faint whispers of oxygen, the world inched closer to something profoundly new. Not a sudden, cataclysmic leap, but a slow, deliberate rebalance, a quiet evolution unfolding molecule by molecule, tide by patient tide. The atmosphere would not transform overnight, nor would life. But the trajectory was irrevocably set. The Earth was not static. It was already preparing for its next grand chapter, when tiny organisms would leave visible marks, and the story of life would finally break the surface. Beneath the heavy, hazy skies and the quiet, enigmatic oceans of the Archean, Earth's interior was anything but still. The planet pulsed with heat, not just a comforting warmth, but a deep, structural fire radiating from its very core. This immense internal heat was not a mere lingering annoyance from its formation. It was a dominant driving force, shaping every aspect of the planet's early behavior. Volcanism was not an occasional event. It was a constant, relentless symphony. The surface was not settled. It was in perpetual motion, flexing, cracking open and reforming again and again, in cycles that profoundly defined this primordial world. The mantle, that vast churning layer of rock nestled between the crust and the core, was hotter and far more mobile than it is today. Convection currents, like colossal unseen rivers of molten rock, rose and fell through it with greater intensity, efficiently transporting heat upward, relentlessly driving volcanic activity and recycling materials between the surface and the deep earth. The crust, where it managed to exist, was thin and fragile by comparison. It had not yet thickened into stable land masses, and what solid surface there was often succumbed to immense pressure, cracking or melting back into the eager mantle. This resulted in a planet with a fractured dynamic surface, a patchwork quilt of volcanic islands, unstable continental fragments, and immense expanses of open ocean. Lava flows were commonplace, forming new crust that might endure for a few million years before being subducted or melted once more. Entire regions could rise, cool, and then disappear beneath the waves, only to be replaced by new volcanic zones elsewhere. It was not a tidy process. It was not even predictable. It was molten, moody, and utterly relentless. Much of this fervent activity unfolded at what might be termed proto-mid-ocean ridges and nascent hotspots, places where magma ceaselessly welled up from below to forge new crust. Some of these features may have borne a resemblance to modern equivalents, such as the Mid-Atlantic Ridge or the Hawaiian hotspot, but on a scale that was far more active, more frequent, and arguably more intense. Without the thick, well-defined plates and boundaries of today's sophisticated tectonic system, these upwellings created crustal patches that moved irregularly, collided unpredictably, and sometimes simply sank back into the mantle before they could ever achieve true stability. Volcanoes were not merely isolated cones. In many regions, entire landscapes were dominated by volcanic forces, massive flood basalts, expansive rift zones, or sprawling chains of submarine eruptions that meticulously built temporary islands. The eruptions themselves varied from slow, effusive lava flows like molten rivers to explosive gas-charged events that spewed ash and gases into the thick, primordial atmosphere. These eruptions profoundly shaped the chemistry of the air and oceans, contributing gases like carbon dioxide, sulfur dioxide, and water vapor, as well as trace elements such as chlorine and fluorine that would participate in further intricate reactions at the surface. On land, to the extent that land existed, the results were ephemeral. Basaltic plains formed, patiently eroded, and then reformed. Rock cooled slowly under the oppressive, thick atmosphere, and chemical weathering was limited by the complete absence of vegetation. Without roots to fracture rocks or organic soil to absorb water, the landscape was sculpted almost entirely by the relentless forces of rain, tides, and gravity. Slopes collapsed, lava hardened, then cracked anew. It was a dynamic, temporary, and profoundly unstable surface, one that rarely persisted long enough to achieve permanence. Even underwater, the planet's mood remained volcanic. Hydrothermal vents punctuated the seafloor, particularly near spreading center. These vents spewed mineral-rich, superheated water into the surrounding ocean, creating localized ecosystems and unique chemical environments. Today, similar vents sustain entire communities of life, from bacteria to tube worms, that rely on chemical energy instead of sunlight. In the Archean, such environments may have been among the most stable habitats available, warm, protected, and rich in nutrients, offering a vital refuge in a world otherwise dominated by pervasive heat and constant flux. All of this grand geological theatre unfolded beneath a sun that did not shine quite as we are accustomed to. The sun during the Archean was approximately 70 to 80% as bright as it is today. It was still a nascent star, only a few 100 million years into its stable main sequence phase. This difference in brightness, while not sounding extreme, had profound consequences. Less solar energy reaching Earth implied a cooler baseline temperature, requiring something substantial to compensate for the shortfall. That crucial compensation, as mentioned earlier, arrived in the form of potent greenhouse gases, most notably carbon dioxide and methane. Without their insulating embrace, the oceans would have remained perpetually frozen despite all the internal heat. But with a sufficiently dense atmosphere, persistent volcanic outgassing, and enough biological methane production, the Earth managed to maintain liquid water and a largely temperate surface, though always poised on the brink of tipping one direction or the other. And while the sun's overall brilliance was diminished, it was also more active in other ways. Young stars tend to unleash more frequent solar flares and intense ultraviolet radiation, without an ozone layer to filter it. This damaging UV light would have struck the surface more directly, especially at higher elevations, and under clear sky conditions. This created a peculiar contrast, a world with lower total visible light, yet higher exposure to certain harmful wavelengths. The planet was simultaneously underlit and overexposed. This faint but volatile sunlight meant that daily and seasonal rhythms were profoundly different from what we experience today. The sky may have been more often overcast, filtered through persistent clouds and atmospheric haze. Sunlight would have reached the surface as a duller, more scattered glow, not the vibrant blue sky days we now take for granted. Sunrises and sunsets might have appeared redder, longer, and strangely ethereal. The sky itself, in the absence of modern air composition, might have boasted hues difficult to predict, with theories ranging from orange-tinted daylight to persistent high-altitude hazes that muted everything beneath them. The brevity of each day, still shorter than ours, dictated the sun's faster arc across the sky. Days passed more quickly, with nightfall arriving sooner and mornings emerging in a tighter, more urgent rhythm. The moon, still much closer to Earth at this juncture, would have dominated the night sky, appearing larger and far more prominent than it does today. Its tidal effects were considerably stronger, its light more significant, and its gravitational presence more central to Earth's geophysical balance. The combined result was a world of striking contrasts. Earth constantly moving between molten instability and the slow emergence of cooling order, between volcanic creation and erosive breakdown. The sun, though diminished, pulsed light and radiation into a dense and complex atmosphere. Oceans boiled near vents and cooled near shadowed shores. The land was perpetually new, yet rarely stable. It was a place of perpetual transition, never quite the same from 1 million years to the next, and certainly utterly unrecognizable by modern standards. And yet, through all this tumultuous flux, rudimentary structures began to form. Rocks hardened, islands persisted long enough to accumulate new sediments. Ocean chemistry began its slow dance of responding to biological input. The relentless repetition of volcanic cycles etched patterns into the crust. The immense energy released from the mantle found outlets that slowly shaped basins, ridges, and perhaps even primitive plate boundaries. Geologists, meticulously studying Archean rocks, can still discern some of these ancient truths, not through photographs or direct observation, of course, but in the intricate textures, compositions, and structures miraculously preserved within ancient formations. Pillow basalts, formed by underwater lava flows, still retain the rounded shapes of their submarine birth. Komatiites, those rare ultramafic volcanic rocks that could only form under extremely high temperatures, whisper tales of a much hotter mantle. Folded greenstone belts reveal regions of crust that were violently squeezed and buried, then later exposed by the slow hand of erosion or tectonic uplift. Even when the evidence is fragmented, the patterns remain remarkably consistent. The Earth in the Archean was not simply chaotic. It was in purposeful motion, under immense pressure, and constantly reshaping its very being. Every eruption, every plume of heat, every rift in the crust contributed to a long, slow process of maturation, not towards perfection or even absolute stability, but towards a profound complexity, towards a world that could eventually sustain more than just lava and microscopic life. We often perceive modern geological activity, earthquakes, volcanic eruptions, tectonic shifts, as rare or disruptive events. They command our attention precisely because they are uncommon in most places. But in the Archean they were the norm, they were not exceptions. They were the fundamental rule. The planet had not yet cooled sufficiently to quiet its fervent internal engine. Its deep heart was still revving, and the surface bore the indelible marks of its every powerful move. That restless, fiery energy did not merely sculpt the rocks, it profoundly shaped the chemistry of the atmosphere and oceans, nurtured the earliest forms of life, and ceaselessly recycled the very materials that would make complex life possible in later eons. It stirred the primordial pot, so to speak, intricately mixing minerals, heat, and liquid water over timescales vast enough for biology to take root. And while we often celebrate the serene stability of the present Earth, with its steady seasons, blue skies, and reliable crust, it was this earlier, more temperamental version that meticulously built the foundational framework. A hotter Earth, a dimmer sun, and a landscape in perpetual revision. Molten moods that slowly solidified into the roots of future mountains. Midnight suns that cast a faint but persistent light upon the path ahead. The world would not remain this way forever. The crust would thicken, the atmosphere would evolve, life would push outward and upward. But in this foundational part of Earth's story, everything remained in flux, not random, but not yet fully ordered, and somewhere in all that motion, the planet continued its arduous building, one eruption, one cooling cycle, one shifting plate at a time. The powerful rhythm of change had been, and it showed no signs of slowing down. Even in a world as volatile as the Archean, there were moments of profound quiet. Not peace, perhaps, but shifts in rhythm, subtle changes in energy where something profoundly new could begin. One of those transformative shifts arrived with the slow, patient cooling of the atmosphere, when temperatures finally descended enough for water vapor to condense, gathering into thick clouds and falling from the sky. The first rain did not arrive with ceremony. There were no nascent plants to catch its gentle fall, no soil to absorb its touch, no animals to scatter from its path, only volcanic rock, stark and hot, meeting water that had once been steam, a primordial encounter. The early atmosphere was perpetually saturated with vapor, a direct consequence of constant outgassing from the planet's interior and from the surface itself, which still radiated immense heat. As the planet continued its slow, patient cooling, that vapor condensed, eventually forming clouds dense enough to produce precipitation. This was not a singular event, a grand cosmic deluge. It likely unfolded over and over again, in pulses and waves, as different regions of the atmosphere passed through cycles of heating and cooling. But over immense spans of time, enough rain fell, again and again, to begin filling the lowest points in the landscape. Depressions in the crust, sculpted by tectonic motion or volcanic collapse, slowly began to collect runoff. The result was not a clean, abrupt transition from dry to wet. It was more akin to a gradual soaking, a pervasive saturation of the surface that formed puddles, then lakes, then vast, nascent oceans. The very first raindrops likely evaporated almost instantly upon contact, hitting hot rock and transforming immediately back into steam. But as the crust slowly cooled and stabilized, more of that precious water remained liquid. Pools lingered longer, flow paths began to etch themselves into the barren landscape, and eventually the surface reached a tipping point, enough liquid water to maintain itself, perpetually recycling between sky, land, and sea in something resembling a nascent hydrological cycle. This was a monumental turning point, even if no conscious entity existed to witness its quiet grandeur. Rain did not merely cool the surface, it began its profound work of shaping it. The falling water ceaselessly eroded rock, carved channels, transported sediment, and participated in intricate chemical reactions that would define the planet's surface chemistry for billions of years to come. It was not rain in the comforting way we perceive it now. There was no soft patter on rooftops, no storm drains or rivers bordered by trees, yet the fundamental physics remained the same. Gravity pulling condensed moisture from clouds to ground, heat driving evaporation, and pressure systems pushing moisture through the vast atmosphere. Rain was also an integral part of the delicate feedback loop that regulated planetary temperature. As water vapor condensed, it released latent heat into the atmosphere, warming it subtly and influencing cloud formation. Clouds themselves reflected incoming sunlight, contributing to a vital cooling effect. And as rain fell upon the hot volcanic rocks, it began its slow, intricate dance of reacting with minerals, triggering chemical weathering processes that would eventually draw carbon dioxide out of the atmosphere and meticulously lock it into the crust. These weathering reactions were particularly significant because they marked one of the first large-scale mechanisms by which Earth began its long, patient journey of regulating its own climate. Volcanism relentlessly pumped CO2 into the air, and weathering, with equal persistence, slowly pulled it back out. Not immediately, not evenly, but gradually, over immense timescales. This delicate balance was instrumental in maintaining conditions suitable for the persistence of liquid water. Even with a faint sun and an atmosphere that was still in its formative stages, the surfaces that received the rain were mostly basaltic, dark, dense volcanic rock formed from cooled lava. These rocks possessed high surface temperatures and a chemical composition rich in magnesium, iron, and calcium. When rain fell upon them, it triggered reactions that formed clays and carbonates, subtly altering the landscape both physically and chemically. Over time, these altered rocks contributed to the formation of sediments that settled into basins, commencing the earliest geological layering processes. Rainfall also initiated mechanical erosion, not on the grand scale we now associate with braided rivers and majestic canyons, but with small-scale movements, material being loosened, transported downhill, and deposited elsewhere. In this way, the very first stages of sedimentary geology were born. Even in a world utterly devoid of soil, the water was carving, sorting, and relocating minerals. As this process unfolded across myriad regions, the low-lying areas became natural gathering points for water. With sufficient accumulation, these basins gradually transformed into the first long-term bodies of water, what we might tentatively call oceans, though their boundaries were still in a constant state of flux. The early oceans were likely acidic, rich in minerals and warm, with distinct layers of temperature and chemistry. They were not stagnant. They moved with the inexorable pull of tides, the gentle push of wind, and the unseen currents, especially as the moon, still close and profoundly influential, stirred the water with a stronger gravitational pull than it exerts today. These early oceans did not merely reflect the planet's heat and light. They began to host a complex chemistry that had nowhere else to go. Molecules suspended in rainwater, gases dissolved from the atmosphere, minerals leached from rocks. All of it eventually found its way into the oceans, and there it mixed slowly, perhaps randomly at first, but gradually, with patterns that emerged over time. The oceans became a vast planetary laboratory where temperature gradients, chemical gradients, and the relentless passage of time meticulously created the conditions for increasingly complex reactions. It is within this primordial context that life took its tentative, yet tenacious hold. The persistent presence of standing, circulating water made it possible for organic molecules to form, to concentrate, and to interact. Small-scale wet-dry cycles on land may have contributed as well, evaporation concentrating compounds in shallow pools, rain bringing in new materials, and heat driving synthesis. But the oceans were the main stage, both for the chemistry of life and for the earliest microbes that would slowly evolve from it. Rain was the ultimate delivery system, the crucial starting point for those cycles. It intricately connected atmosphere to crust, sky to sea. Without it, water would have remained vapor, chemistry would have remained diffuse, and life would have struggled to gather the materials it needed in one concentrated place. With rain, the world entered a new phase, one where the surface could host persistent environments, not just transient reactions. And yet, there was still no true land as we know it. The few fragments of crust that managed to rise above the sea were barren and dark. No roots held them together, no vegetation stabilized their surfaces. Rain falling on these nascent islands simply ran off, picking up minerals and carrying them inexorably to the sea. Over time, this runoff subtly altered ocean chemistry, adding calcium, silica, and other elements that would later become critically important for biological processes like shell building and internal cell structure. There is some fascinating debate about precisely how much land was exposed at this time. Some models suggest that the early Earth was almost entirely ocean-covered, with only scattered volcanic islands or small proto-continents. Others argue that larger areas of land may have existed intermittently, rising and falling with tectonic shifts. Either way, rain was an integral part of that dynamic process, eroding highlands, depositing sediments in lowlands, and participating in the long-term cycling of materials between land and sea. Even the very process of rain itself helped to cool the earth. As water condensed and fell, it carried latent heat from the atmosphere to the surface, where it could be released and radiated into space. This ongoing exchange played a crucial role in maintaining the climate within the range needed for habitability. Without rain, Earth's surface might have remained too hot, too chaotic, or too chemically limited to support stable life. That does not imply that early rain was gentle or predictable. Without vegetation, storm systems likely formed and dissipated quickly, driven by sharp temperature gradients between day and night, land and sea. Thunderstorms may have been common, with lightning serving as another potent energy source for atmospheric chemistry. Each flash delivered a powerful jolt that could break apart molecules, reform bonds, and drive the creation of new compounds in the air and on the ground. There is evidence that such processes significantly contributed to the prebiotic chemistry that made life possible, not just in the oceans, but in the atmosphere and on wet surfaces. The intricate interaction of lightning, water, and gases could form amino acids, sugars, and other organic compounds. Some of these vital materials would have washed into the sea with the rain, where they might be taken up by evolving biological systems. The story of rain in the Archean, then, is not merely about water, it is about profound interaction. Rain marked the genesis of large-scale surface processes, erosion, sedimentation, chemical cycling processes that continue to shape our planet today. It enabled life to persist and to slowly expand. It allowed the crust to communicate with the ocean, and the ocean to feed back into the air. It brought the planet's systems into intricate connection with each other, drop by patient drop, and once that fundamental pattern began, it never truly stopped. Rain became an intrinsic part of Earth's identity, not always predictable, not always the same, but always present. A constant, vital thread running through the planet's immense history, intricately linking fire to water, gas to rock, and chemistry to biology. As the rains continued their ceaseless fall and the oceans deepened, the crust responded. Islands rose, gracefully sank, and rose again. Some regions began a slow process of stabilization, others fractured anew, and in the warm, mineral-rich waters near those nascent shores, microbes were beginning to construct something profoundly new. Not merely intricate chemical networks or ingenious survival strategies, but physical structures, tangible traces, silent signs that life was no longer simply reacting to the world, but was actively beginning to shape it. The next quiet revolution was already well underway. Even as the relentless rains carved their ancient channels and the oceans gathered their chemical memories, something deeper was shifting, a slow, profound recalibration. Beneath the basaltic crust, the mantle continued its eternal churn, a vast, unseen engine of slow, uneven energy. Heat surged upward in colossal columns. The thin plates of crust, fractured and inherently unstable, responded in fits and starts, like a sleeper stirring from a deep dream. There were no continents in the modern sense, no expansive, familiar shelves, no sweeping mountain chains reaching for the sky. Yet, the foundational pieces were there, scattered and moving in ways that tantalizingly hinted at something far grander to come. This was not continental drift as we know it. Not yet, not in its refined, familiar form. The Earth's lithosphere during the Archean was hotter, thinner, and far more ductile. Tectonic motion certainly existed, but it lacked the organized structure and predictable grace of the modern plate system. Instead of vast, defined plates gliding across a relatively rigid surface, the early crust likely fractured more easily, forming smaller, more ephemeral blocks that moved irregularly, collided unpredictably, and sometimes simply melted back into the ever-hungry mantle. These nascent blocks, the venerable precursors to modern continents, formed from a complex interplay of volcanic activity, crustal thickening, and repeated cycles of burial and remelting. In some fortunate areas, new crust rose from the mantle, slowly cooled, and began its patient accumulation. When two such blocks eventually collided, their edges could be crumpled and thickened, forming more stable fragments that stubbornly resisted further melting. These resilient fragments sometimes endured long enough to begin developing a kind of identity thicker, lighter, more chemically differentiated than the surrounding oceanic crust. We call these ancient fragments cratons. They are the oldest, most stable, and most resilient parts of Earth's surface, the deep, enduring roots of continents that would emerge much later. Cratons formed not in a single dramatic event, but gradually, through repeated episodes of crust formation, magmatic intrusion, and intense high-pressure metamorphism. Over immense spans of time, they cooled, thickened, and became mechanically stronger. Unlike younger, more flexible crust, cratons do not subduct easily. They float higher on the mantle, like ancient rafts, and stubbornly resist being recycled back into the planetary interior. You can still discover these ancient cratonic regions today, scattered across the globe like geological fossils: the Canadian Shield, the Pilbara and Yilgarn blocks of Australia, the Kapfile Craton in South Africa. All of them began their slow stabilization during the Archean. When geologists study these hallowed areas, they are peering directly into the Earth's deep, primordial past, touching the very remnants of its first long-term land. The movement of these early blocks was far from smooth. Some may have drifted apart, lost to the deep currents of the mantle. Others collided and stubbornly stuck together. The intense mantle heat beneath them drove episodic magmatism, vast pulses of volcanic activity that meticulously built up new layers of crust. In places where the crust grew thick enough, it began to insulate itself from the fiery heat below, cooling more slowly, resisting deformation. These regions started behaving more like true continents, staying above water, enduring the relentless forces of erosion, and forming the higher points in a largely ocean-covered world. But they were not yet continents in the full, majestic sense. They lacked fixed shapes or definitive boundaries. They were not permanent fixtures of the surface. Some may have persisted for a few 100 million years, others for only a few tens. The profound difference between oceanic and continental crust was not yet as sharply defined as it would become. The intricate processes that made continental crust thicker and more buoyant, such as the formation of granitic rocks, were just beginning to accelerate. Much of the Archean crust was still mafic, meaning rich in magnesium and iron. This made it denser and more prone to recycling back into the mantle. Over time, through partial melting and chemical differentiation, felsic rocks began their slow accumulation, rocks with more silica, lighter in color and density, and inherently more likely to float and persist. These felsic components are absolutely essential for building stable continental landmasses. Their gradual increase marked a pivotal turning point in Earth's geological evolution. The resulting landscape was profoundly fragmented. Islands and microcontinents rose above the waves, only to be patiently worn down by weathering or reabsorbed by relentless tectonic forces. Some clustered into larger landmasses, others remained isolated, like solitary thoughts in a vast mind. The view from above, had there been an eye to witness it, would have revealed scattered landforms within an immense ocean, with only faint hints of the continents we recognize today. Nothing was in its final place. Everything remained temporary, in motion, still deciding its ultimate direction. Despite their inherent impermanence, these early land fragments began to engage in crucial interactions with the oceans and atmosphere. Exposed rock underwent weathering, releasing ions into the water and actively participating in the nascent carbon cycle. Sediments eroded from these proto-continents, settled into nearby basins, layering into formations that would eventually become the indelible record of the Archean. In some regions, stable shelves began to develop, where repeated deposition created thick successions of sedimentary and volcanic rock. These regions now appear in the geological record as greenstone belts, sequences of metamorphosed basalt, volcanic ash, and sediment that were deposited in Archean basins and later squeezed and folded by immense tectonic collisions. Greenstone belts are among the best preserved windows into the Archean Earth, providing compelling evidence of early tectonic processes, fervent volcanic activity, and unique sedimentary environments. Their formation suggests that even if full-plate tectonics hadn't yet fully taken shape, something akin to it was profoundly underway. The processes driving crust formation and movement were episodic, bursts of intense activity followed by quieter contemplative periods. Heat flow from the mantle may have been concentrated in plumes, driving localized melting and crust formation rather than global-scale motion. Subduction, where oceanic crust gracefully sinks back into the mantle beneath another plate, may have occurred in isolated zones rather than along continuous margins. The Earth was, in essence, experimenting with different geological strategies, some of which would endure, others of which would gently fade away. At the surface, all of this ceaseless movement created new environments for the stirrings of life. Shallow marine basins, volcanic shorelines, tidal flats, each offered different, yet specific, conditions for microbial growth and preservation. When land rose above the waves, it exposed new minerals, allowed for new chemical reactions, and offered vital substrates for microbial mats. These mats, formed by intricate communities of bacteria, began to trap and bind sediments, leaving behind layered structures that would later become stromatolites. The emergence of semi-stable land surfaces also implied new, profound interactions with the atmosphere. Rain falling on exposed rock triggered increased weathering. Runoff carried precious nutrients to the sea. The air, oceans, and crust were becoming increasingly interconnected. With each cycle of erosion and deposition, new materials entered the system. Some were meticulously locked into rock, others returned to the water, where life could utilize them or transform them. At the same time, internal processes continued their relentless reshaping of the crust from below. Magma intruded into older rock. Crustal fragments sank, melted, and reformed. High temperatures and pressures created metamorphic rocks, restructured versions of earlier crust that recorded the story of their formation in intricate mineral textures and compositions. These rocks, now found in ancient shields around the world, are among the oldest pieces of Earth still in existence. What they reveal is not a static picture, but a restless, dynamic one. The Earth was already experimenting with continental behavior, patiently striving to build something that would endure. Some fragments succeeded, others failed. But through all of it, the average crustal composition was undergoing a slow, profound transformation. More silica, more aluminum, more of the very elements that define continental material. The planet was slowly learning how to build land that could stay put. There is no single definitive moment when continents began their grand journey. It was not an event, it was a process, one that stretched across hundreds of millions of years. The Archean was a time of cosmic testing, assembling the pieces and beginning to tentatively move them. The motion was real, but not yet refined. The fragments were mobile, but not yet fully plate-bound. It was continental drift in an early experimental phase, slow, erratic, and often undone. Still, the direction was unmistakably clear. Earth was building towards something more coherent. The crust was thickening. The land was enduring longer. The rocks were recording more history. And even as the continents hesitated, gathered, or dissolved, life was adapting to every shift. The oceans, fed by this changing land, were becoming more chemically complex. The environments around volcanic shores and greenstone basins were richer in nutrients. The world was starting to settle, just a little, not because the heat had vanished, it hadn't, not because the crust had ceased its movement, it had, but because the systems were beginning to cooperate. The deep mantle, the shallow seas, the thickening crust, and the microbial biosphere were no longer acting independently. They were intricately entangled, sharing matter and energy in cycles that grew more efficient with each iteration. And with that growing interaction came new profound consequences. Microbes were not just surviving now, they were leaving behind traces, structures that could persist in the rock record, subtle changes in the chemical composition of sediments, and in some places visible signs that life was beginning to shape the surface, not just react to it. Those signs, slowly built in tidal pools and shallow seas, would mark the next pivotal step in this unfolding story, the moment when biology began to assume a more visible, active role, not with complexity or grandeur of size, but with sheer, stubborn persistence. The surface of the Earth was ready to be written on. Life had started writing. There's a common tendency when we conjure images of volcanoes to picture majestic, snow-capped cones, perhaps gently puffing steam at their summits, or spewing dramatic clouds of ash against a serene blue sky. But in the Archean, volcanoes were not mere landmarks. They were the very background hum of existence. There weren't just a few, they were ubiquitous, constant, unrelenting. The Earth's crust in this period was as much about what incessantly surged forth from the mantle as what managed to precariously solidify and remain on the surface. The planet's internal heat was still immense. Radioactive decay within Earth's deep interior, a process that releases energy over vast spans of time, was far more intense than it is now, simply because a greater proportion of the unstable isotopes responsible was still present. That colossal energy had to find a way to escape, and the surface was its primary conduit. The result was a world in which volcanic activity was not just common, it was absolutely essential. New crust was born, almost entirely through the relentless force of volcanism. Ocean floors spread with effusive basaltic flows. Volcanic islands majestically rose, dramatically collapsed, and reformed anew. Submarine eruptions blanketed seafloors with fresh material, layering over and over again in sequences we can still discern today in the intricate greenstone belts. On land, to the extent that land existed, lava ceaselessly reshaped the surface with each eruption. Volcanoes were not rare disruptions, they were the planet's default setting. Many of these eruptions did not occur on what we now perceive as dry land. They unfolded predominantly underwater. The majority of the planet remained ocean-covered, and mid-ocean ridges and volcanic arcs stretched for thousands of kilometers beneath the waves. Here, lava extruded into the surrounding water, cooling rapidly into pillow basalts, rounded, bulbous formations that exquisitely preserve the shapes of underwater flows. These unique pillows still appear in ancient rocks, direct evidence that Archean volcanism happened just as often, if not more so, beneath the sea as it did above. The chemistry of these eruptions also varied. Most produced mafic lava rich in magnesium and iron, low in silica. Mafic lava flows easily, spreads quickly, and typically doesn't result in explosive eruptions unless significant gas is heavily involved. But in the Archean, some lavas were even more extraordinary. One of the most distinctive volcanic rocks from this era is komatiite. These ultramafic rocks formed from lava that was vastly hotter than anything we observe on the modern Earth, possibly exceeding 1,000. Komatiites are profoundly significant because they only formed when the mantle was hot enough to produce such extreme melts. They contain exceptionally high levels of magnesium and exhibit unique flow structures that indicate incredibly low viscosity. You won't find komatiites forming today. Earth's mantle simply isn't hot enough anymore. But in the Archean, they were relatively common, marking places where deep mantle plumes reached the surface with tremendous, unbridled energy. Volcanoes did not merely build crust, they profoundly altered the atmosphere. With every eruption, vast quantities of gases were released. Not just carbon dioxide, but also sulfur dioxide, water vapor, hydrogen sulfide, and other volatiles. These gases contributed significantly to the planet's early climate, influencing temperature, atmospheric pressure, and even the very composition of rainfall. Sulfur gases, in particular, exerted a powerful effect, forming aerosols that reflected incoming sunlight and affected cloud formation. The delicate balance of greenhouse gases and reflective particles created a complex, constantly shifting climate. Large-scale eruptions could paradoxically cool the surface by injecting sulfur aerosols into the stratosphere. Smaller eruptions might warm it by releasing more carbon dioxide. The profound absence of oxygen meant that some of these gases persisted longer than they would today, participating in long-term chemical cycles that were only beginning their slow stabilization. Underwater, volcanic activity gave birth to intricate hydrothermal vent systems, not just isolated chimneys, but entire fields of vents. These were places where seawater percolated down through hot rock, became superheated, and then surged back into the ocean, carrying dissolved minerals and chemicals. Around these vents, life flourished, not photosynthetic life, but chemosynthetic microbes that utilized the chemical energy from reduced compounds like hydrogen sulfide to construct organic molecules. These vent communities may have represented the earliest analogues to complex ecosystems, complete with producers, recyclers, and waste processors, all operating on a purely chemical level. The energy flow from the mantle through these volcanic systems may have made life not only possible, but sustainably resilient. Volcanic islands, when they did manage to rise above the ocean's surface, created entirely new environments. Their surfaces cooled quickly, but their interiors retained immense heat. Rainwater falling on fresh basalt reacted with minerals, initiating crucial weathering processes. Erosion carried material back to the sea, enriching the surrounding waters with vital nutrients and subtly altering local chemistry. These islands were temporary, ephemeral, but while they endured, they added crucial variety to the surface, high points, ridges, slopes, and basins that simply did not exist in the open ocean. Sometimes these islands collided with other crustal fragments, beginning the slow process of forming larger landmasses. These collisions often triggered even more volcanism. Magma intruded into existing rock, creating new mineral combinations and heating the crust from below. These processes were integral to the early continental growth cycle, a repeating pattern of eruption, thickening, metamorphism, and gradual stabilization. In places where volcanic arcs formed, similar to modern island chains like Japan or the Aleutians, repeated subduction and magmatism meticulously built up significant crustal thickness. These arcs may have been among the first long-lived land regions, their structure formed by oceanic crust diving beneath other oceanic crust, creating the kind of repeating volcanic systems that could accumulate material over immense periods. And yet, none of this was permanent. Subduction often recycled crust back into the mantle. Whole volcanic provinces may have formed, grown, and vanished in less than 100 million years. The Archean Earth was a system still desperately striving to find equilibrium. The processes that governed it, volcanism, tectonics, erosion, were familiar in principle but profoundly different in scale, temperature, and timing. Geologically, the evidence for all this comes not just from volcanic rocks, but from the metamorphic zones surrounding them. High-grade metamorphism where rocks are buried and profoundly altered by heat and pressure, is common in Archean terrains. It reveals that volcanic regions were not only intensely active, but also deeply affected by crustal thickening and tectonic stacking. These events produced rock textures and mineral assemblages that point directly to a hot, dynamic, and constantly evolving surface. Even today, Archean volcanic rocks are among the most meticulously studied for their mineral potential. The very processes that built them often concentrated valuable elements, gold, nickel, copper, in ways that modern mining operations still diligently pursue. These economic interests drive much of the detailed research into Archean geology, helping to meticulously map out the structure of rocks that have miraculously survived billions of years of weathering and tectonic distortion. Even beyond their economic value, these ancient volcanic systems reveal something fundamental about the early Earth: that the surface we walk on now, so seemingly solid and settled, was once fluid, fiery, and under constant fervent construction. Volcanoes were not just a feature of the landscape, they were the architects. They helped meticulously build the first continents, profoundly contributed to the early atmosphere, sustained the first delicate ecosystems, and participated in global cycles that would eventually lead to a planet with stable climates, a protective ozone layer, and breathable air. And all of that began here, not in silence but in eruption, in the primal roar of heat meeting rock, gas meeting ocean, and chemistry meeting biology. As the volcanic surface continued its ceaseless shifting, the nascent life around it adapted with profound resilience. Microbes colonized new lava flows, flourished in sediments formed from ash, and discovered thriving niches near vents and hot springs. Earth's surface was a dangerous realm, but it was also incredibly rich. Each eruption, each new flow of basalt or komatiite, brought more material into the cycle, more rock to weather, more nutrients to carry, more heat to harness, and gradually, in the liminal margins between land and sea, something else began to take shape. Not just microbial mats or chemical signatures, but physical structures, tangible traces that would endure, evidence that life wasn't just surviving now, it was actively beginning to build. And once life starts leaving its indelible marks in stone, it becomes an intrinsic part of the geology, no longer just a passive passenger. That's where our journey will lead us next. The Earth we inhabit today boasts a distinct, vibrant palette: cerulean skies, billowing white clouds, verdant green forests, and oceans of deep navy. It is a familiar, expected, even comforting aesthetic. But during the Archean Eon, the planetary color scheme was something else entirely. The skies were not blue. The seas were not clear. The world had not yet settled into its modern, tranquil beauty. If you could have somehow stood on an Archean shoreline, assuming you could miraculously survive the toxic air, what your eyes would have beheld might not resemble anything we associate with Earth today. Let us begin with the oceans, those vast liquid cradles of nascent life. By the Archean, water had already enveloped most of Earth's surface. The seas were immense, persistent, and chemically hyperactive, but they were not the sparkling blue expanses we imagine now. The profound absence of oxygen, both in the air and dissolved in the water, fundamentally altered everything. In the modern ocean, oxygen interacts readily with iron, binding it into insoluble forms that gracefully sink to the bottom, leaving the water relatively clear. In the Archean, that intricate process had not yet begun. Without free oxygen, iron remained freely dissolved in the ocean in high, pervasive concentration. This imparted to the water a distinctly different appearance, likely green, possibly even verging on brown in some regions, depending on the complex mix of metals and sediments. Iron-rich water naturally possesses a greenish tint, especially when combined with other dissolved minerals. In areas near hydrothermal vents or active volcanic islands, the color may have deepened further due to additional inputs of elements like sulfur or silica. Photosynthetic organisms had already emerged by this time, including the pioneering early cyanobacteria, but they had not yet achieved the global transformation of the planet's chemistry. Their nascent oxygen, produced through the intricate dance of photosynthesis, was still being voraciously absorbed by the vast oceans and by the omnipresent iron-rich rocks. Until those immense sinks were fully saturated, the oxygen remained locked away, and the ocean remained stubbornly anoxic, a term meaning without oxygen that defined not just the biology but the entire chemical environment. This pervasive lack of oxygen allowed for the persistent presence of other compounds that are fleeting in today's oceans. Hydrogen sulfide, for example, may have accumulated in certain areas, particularly in deeper or poorly mixed water. Combined with iron, this could create distinct layers of chemically stratified water. Surface waters, gently stirred by wind and sunlight, may have possessed a different chemistry than deeper regions fed by hydrothermal activity and sediment decay. These distinct layers would have profoundly affected not only the color of the ocean, but also its biological potential. Life in the surface layer would have needed to bravely cope with intense UV radiation and low oxygen. Life in deeper waters would have faced immense pressure, minimal light, and possibly toxic concentrations of sulfides. The result was a patchwork quilt of environments, some welcoming to nascent life, others intensely hostile, but all intricately interconnected. Above the ocean, the sky was not the deep, familiar blue we associate with a clean, oxygen-rich atmosphere. That comforting color originates from the way nitrogen and oxygen scatter sunlight, specifically blue wavelengths, through a process known as Rayleigh scattering. But in the Archean, the air was profoundly different. There was nitrogen, yes, but little to no free oxygen. The atmosphere was denser, heavily laden with gases from persistent volcanic outgassing, including carbon dioxide, methane, water vapor, and possibly ammonia. Methane, in particular, exerted a strong influence on how sunlight permeated the atmosphere. In high concentrations, it could create a pervasive haze, not unlike what we observe on Saturn's enigmatic moon Titan, that scattered light in fundamentally different ways. Instead of blue, the dominant scattering may have favored reddish or pinkish hues, especially at sunrise and sunset. Combined with a fainter sun and possibly high-altitude clouds or sulfur-based aerosols, the visual effect could have been truly dramatic. The term hazy applies here, not just visually, but chemically. The Archean sky was a reactive, dynamic environment. Sunlight striking methane could trigger complex photochemical reactions, breaking it apart and forming more intricate hydrocarbons, some of which would condense into airborne particles, further thickening the haze. This photochemical smog would have filtered sunlight, altered the planet's albedo, its reflectivity, and contributed to either warming or cooling depending on its density. That pervasive haze might have provided a crucial protective shield for early life from damaging UV radiation, acting as a kind of crude planetary sunscreen. Without an ozone layer, which today is formed from the intricate interaction between oxygen and UV light, the surface would have been relentlessly exposed to high levels of damaging ultraviolet rays. Any shielding, even from organic haze, could have made a significant difference for surface-dwelling or shallow water organisms. It's also plausible that this methane haze fluctuated over time. Changes in microbial activity, immense tectonic events, or shifts in temperature could alter methane production or destruction, creating periods where the haze thickened or cleared. Each shift would have affected not just the appearance of the sky, but crucially, how much sunlight reached the surface, with profound potential consequences for climate, ocean chemistry, and biological productivity. The dynamic interaction between the green, iron-rich ocean and the pinkish, hazy sky created a world of unusual, striking contrasts. Where today we encounter familiar color boundaries, blue sky meeting blue sea, green forest stretching to grey mountains, the Archean offered something less uniform, more enigmatic. The sea was darker, the sky was softer or dustier, and the very boundary between them may have been more diffuse, blurred by haze and pervasive humidity. In terms of temperature, the dominant greenhouse gases in the atmosphere, primarily carbon dioxide and methane, were doing most of the heavy lifting. They efficiently trapped heat and meticulously maintained surface temperatures within the range necessary to sustain liquid water, even with a dimmer sun. But this was not a finely tuned system. Periods of volcanic inactivity, shifts in weathering rates, or changes in biological activity could easily tip the delicate balance. Cooling events may have occurred, possibly even localized glaciation in limited regions, though definitive evidence for global freezing during the Archean is still debated. The crucial point is that the climate was not fully stable. It was in a profound state of development, constantly adjusting as the planet's interior slowly cooled, as the crust matured, and as life began to interact more deeply with its environment. The color of the ocean, the intricate chemistry of the air, the very texture of the clouds, all of it was deeply interconnected. Each piece influenced the others, sometimes subtly, sometimes profoundly. Life at this nascent stage was still microscopic. It moved through this strange world in thin films, in suspended mats, in planktonic drifts across shallow basins. It did not require clear skies or pristine water. It required energy, raw materials, and the boundless patience of time. It found those in the boundary zones near hydrothermal vents, in sunlit tidal flats, around nascent volcanic islands. Wherever gradients formed and resources moved, even as the world around it appeared utterly alien by modern standards, life was adapting to it, slowly, patiently shaping it in return. And though we cannot observe it directly, we possess the rock-banded iron formations, which formed when the first traces of oxygen from photosynthetic microbes reacted with dissolved iron in the ocean, provide us with the chemical signature of a green sea slowly, inexorably turning towards something new. Sulfur isotope records reveal that the atmosphere was still anoxic, but undergoing profound chemical change. Carbon isotope data hints at biological productivity increasing in certain regions, perhaps seasonally, perhaps continuous. These indirect records allow us to reconstruct a picture, not with sharp photographic detail, but with compelling consistency. A world where the air carried methane, the water carried iron, and the light filtered through a dusty, enigmatic sky. A planet that was not barren or dead, but profoundly unfamiliar. A working system, not yet refined, and within it biology was not just surviving. It was beginning to leave its indelible patterns, not fossils, not yet, but influence. Those changes would grow. As photosynthetic microbes continued to populate shallow seas and mat-like communities began to stabilize in sediment, the oceans would start to reflect their activity more directly. The haze in the sky would slowly begin to dissipate. The water would embark on its long journey to change color. The entire world, still raw and unstable, would respond, not overnight, not with a sudden roar, but persistently. And eventually, in certain hallowed places, life would begin to construct something physical, not just fleeting molecules, but enduring structures, tangible traces, stacks of sediment bound together by biology, recording its presence in the most durable material Earth has to offer, stone. These would be among the first features to survive into the fossil record, visible even billions of years later. The ocean and sky had meticulously set the stage. Now life was ready to step into view. The very idea of a cradle implies something gentle, something enclosed, something inherently safe. But the Archean Earth offered no such conventional safety. The surface was profoundly unstable, the air utterly unbreathable, the sunlight harsh and unforgiving. Yet somewhere within that volatile world, life not only began, it tenaciously endured. It discovered energy, meticulously built structure, relentlessly replicated itself, and adapted with astonishing resilience. The conditions were not ideal, they were not stable, but they were profoundly sufficient, just enough for something to take hold and refuse to let go. Pinpointing the exact moment life began is an impossible task. The fossil record does not extend far enough back in time, and early biology, existing as simple single-celled organisms adrift in the vast sea, left behind few direct, unambiguous traces. However, the compelling chemical signatures embedded in certain ancient rocks suggest that by the mid to late Archean, more than 3.5 billion years ago, life was already widespread in the oceans, already photosynthesizing in some regions, and already actively participating in the global cycling of carbon, nitrogen, and sulfur. The earliest life was not composed of cells in the intricate way we understand them now. It likely began as simpler, self-replicating systems, molecules capable of copying themselves gently encased by membranes formed from naturally assembling lipids. These rudimentary structures were not alive in the full biological sense, but they performed the necessary functions. They grew, they divided, they competed over immense spans of time through the relentless processes of mutation and natural selection. These proto-life forms slowly evolved into greater complexity, developing the first true cellular structures and intricate metabolisms. The source of vital energy for these early systems depended profoundly on their location. In deep sea environments, the ubiquitous hydrothermal vents offered rich chemical gradients. Stark differences in temperature and composition between the surrounding water and the vent fluids. These gradients could drive the synthesis of organic molecules and provide the raw energy for metabolic reactions. In shallow waters, sunlight emerged as the primary energy source, utilized first by organisms that did not require oxygen, and later by those that began to produce it. Chemosynthesis likely came first, the astonishing ability to convert inorganic molecules like hydrogen sulfide or methane into usable energy and biomass. Microbes thriving near vents still perform this feat today. They require no sunlight, relying instead on specialized enzymes that strip electrons from one molecule and transfer them to another, releasing energy in the process. This kind of metabolism could operate in total darkness within the high-pressure, mineral-rich environments of the deep ocean. Photosynthesis arrived later, though precisely how much later remains a subject of ongoing debate. Some of the earliest known signs of photosynthetic activity appear in rocks dated to approximately 3.5 billion years ago. This early form of photosynthesis may not have produced oxygen. Instead, it may have used hydrogen sulfide or other compounds as the electron donor. Only later, with the profound evolution of cyanobacteria, did oxygenic photosynthesis begin, the revolutionary process that splits water molecules and releases oxygen as a byproduct. That pivotal development, though slow and gradual, would eventually transform the entire world. But at first, the oxygen produced did not accumulate in the atmosphere. It reacted immediately and voraciously with the dissolved iron in the oceans, forming insoluble iron oxides that settled to the seafloor. Over time, this repetitive process created the majestic banded iron formations, layers of iron-rich rock, that still appear in ancient terrains around the world. These rocks are some of the earliest large-scale biological signatures on Earth, formed not from direct fossils, but from chemistry meticulously driven by life. Where did life truly begin its journey? Several compelling candidates exist. Deep-sea hydrothermal vents offer one intriguing possibility: hot, mineral-rich environments where water and rock constantly interact, creating gradients and a steady flow of nutrients. Alkaline vents, in particular, provide natural proton gradients across porous rock membranes, structures not unlike the ones cells utilize today to generate energy. Shallow water environments present another intriguing possibility. Tide pools and coastal flats could have provided crucial wet-dry cycles, concentrating organic molecules through evaporation and mixing them with mineral surfaces that catalyze reactions. The exposure to sunlight and other environmental stresses could have driven evolution, favoring more robust molecular systems. There's also the fascinating idea of life beginning in the subsurface, within the pores and cracks of hot rock, insulated from the harsh surface, but still connected to vital chemical flows. This environment offered protection from intense UV radiation and impact events, while still allowing interaction with water, heat, and minerals. It's entirely possible that life began in one of these environments, and then gracefully migrated to others, as conditions slowly changed. Regardless of its precise origin, by the late Archean, life had spread its invisible tendrils. It occupied a diverse variety of niches: hydrothermal vents, tidal flats, shallow seas. Microbes grew in intricate mats on submerged surfaces, forming layered communities that trapped sediments and created complex chemical microenvironments. These mats were not merely passive aggregations, they actively altered the pH of the surrounding water, changed redox conditions, and influenced the deposition of minerals. In some fortunate places, these microbial mats became stable enough to construct physical structure. As the organisms meticulously trapped and bound sediment particles, they formed domes or layered columns. Over time, these grew into stromatolites, laminated structures that exquisitely preserve the pattern of microbial growth and sediment accumulation. Some of the oldest known stromatolites date to over 3.4 billion years ago, and they appear in rock formations that were once shallow marine environments. Stromatolites are among the first visible, tangible evidence of life actively shaping its environment in a structured, organized way. They demonstrate that life was not just present, but profoundly active, building, modifying, and persistently enduring. These were not isolated events. Stromatolites appear in multiple locations across different parts of the ancient world, in Australia, South Africa, Canada, and beyond. Their global distribution suggests that wherever conditions allowed, these structures emerged independently. They were not confined to a single habitat or event. They represented a successful strategy, a persistent way for life to endure and protect itself. And that strategy proved effective across vast distances and immense timescales. While the forms of stromatolites are remarkably simple, their very presence marks a profound shift. Before stromatolites, life was mostly invisible, a hidden chemical dance. After them, it exerted a tangible physical impact. The seafloor was no longer solely shaped by currents, tides, and sediments. It was also profoundly shaped by biology. Microbial life was not just reacting to its surroundings, it was actively building. In doing so, it began to subtly, yet profoundly change the world around it. Photosynthesis, especially by cyanobacteria, tirelessly produced oxygen. At first, this nascent oxygen reacted voraciously with dissolved iron in the oceans, forming insoluble iron oxides that settled out of solution and created the majestic banded iron formations. But over time, as these immense sinks filled up, more oxygen remained in the water, and eventually began its slow escape into the atmosphere. Stromatolites played a central, visible role in this slow transformation as prominent hubs of microbial photosynthesis. They contributed significantly to the global oxygen budget. Not in a dramatic, explosive way. This was not a revolution, but as a long, steady climb. And the oxygen they released began its slow accumulation, at first locally in the shallow marine waters around the structures, then more broadly as photosynthesis became more widespread and the delicate balance of gases began to shift. This profound shift was not smooth or without consequence. Oxygen is inherently reactive, and its emergence triggered immense changes in ocean chemistry that sometimes destabilized fragile ecosystems. Some anaerobic organisms, those meticulously adapted to life without oxygen, were pushed to more marginal, precarious environments. Others adapted, evolving ingenious new pathways, or simply perished. Oxygen created both profound opportunity and immense disruption, forcing life to fundamentally change or to retreat. But the stromatolites remained for much of the Archean. They were dominant forms of life in the visible landscape, not just living within it, but actively shaping it. They altered water flow, trapped vital nutrients, and created small-scale ecosystems within and around their structures. They were both habitat and organism, environment and inhabitant, intricately combined. They also began to profoundly change the sedimentary record. The laminated textures of stromatolites were distinct from purely physical sediment layers. Their presence marked environments where biology had exerted a clear influence on deposition, a unique geometry preserved by wave action, tide cycles, and seasonal changes in light and nutrient availability. Reading stromatolites is akin to deciphering a diary written in stone, slow, repetitive, but profoundly rich in implication. Even their eventual decay contributed to future life. As stromatolite mats died, they released organic matter into the surrounding sediment. This material became vital food for other microbes, helped to bind sediments, or participated in chemical reactions that shaped the mineralogy of the seafloor. In this way, even death in the stromatolite world became an intrinsic part of the grand construction process. Today, modern stromatolites are rare, but not entirely gone. They exist in isolated, hypersaline environments, places too extreme for most grazing organisms that would otherwise destroy the mats. But in the Archean there were no grazers, no animals to disrupt the surface, no predators to consume the mats. Microbes were free to build, uninterrupted, and build they did. This period, when stromatolites were widespread, represents one of the earliest examples of ecosystem engineering, life altering its environment in a sustained and large-scale way. The structures did not rise quickly, they did not spread rapidly, but they endured, and over time, they meticulously laid the groundwork for future complexity. They altered the chemistry of the ocean, they influenced atmospheric composition, they created conditions in which other organisms, perhaps not yet even imagined, could eventually thrive. And they told a story, not through language, but through form, a humble dome on the seafloor, a gentle ripple in the sediment, a persistent trace of structure where none had existed before. These were not fossils of bodies, they were fossils of behavior, the indelible record of repeated, persistent action, of life adapting and organizing and building over immense spans of time. as Earth moved slowly towards a more oxygenated future. Stromatolites were already an intrinsic part of that profound transition. They had no plan, no foresight, but their ceaseless activity created the very conditions in which more dramatic changes could eventually unfold. The stage was still small, the actors still microscopic, but the cosmic script was beginning its slow, profound shift. The biosphere, once hidden, was beginning to leave its indelible mark, not just in chemistry, but in physical shape. And as the planet changed in response, it opened the door for new forms of interaction between life and rock, life and light, life and the very air itself. What came next would not be immediate, but the trajectory was irrevocably set. Life had found a way to build, and eventually it would learn to build even more. The oceans pulsed with life. The surface was bathed in sunlight. The atmosphere, though alien, had its weather. But what it distinctly lacked, not yet, was breath. At least not the kind that draws air into lungs, pulls oxygen into blood, and fuels muscle and motion. Breathing, in that familiar sense, wasn't even a concept on the table. The world simply hadn't made the air for it yet. There was no shortage of gases in the Archean atmosphere. It was thick with carbon dioxide, heavy with water vapor, laced with methane, ammonia, and sulfur compounds. But oxygen, that essential molecule that defines modern respiration, metabolism, and consciousness, was barely present. Microbes had indeed begun to produce it through photosynthesis. Yes, but the Earth wasn't letting it go free. Not yet. Every atom of oxygen released into the ocean was immediately seized by something else, most often iron. The oceans were saturated with ferrous iron, dissolved and patiently waiting. When oxygen encountered it, the reaction was swift and complete. Ferrous iron became ferric, precipitated out of solution, and gracefully settled to the bottom as rust-red minerals. The oxygen didn't linger, it didn't accumulate, it was used, consumed. Even once the dissolved iron was largely tied up and settled into the rock record as banded iron formations, other immense sinks remained. Volcanic gases readily absorbed free oxygen, organic matter soaked it up during decay, sulfur compounds were oxidized. The intricate chemistry of the early Earth was meticulously built around oxygen's profound reactivity, and for a very long time, hundreds of millions of years, that meant it was rarely allowed to persist. So for billions of years, life managed without it. Anaerobic metabolisms, those that do not require oxygen, dominated the primordial biosphere. Microbes utilized fermentation or relied on ingenious chemical reactions involving sulfur, nitrogen, or hydrogen. Some harnessed light, but not to split water or generate oxygen. Others fed on molecules leaking from the seafloor or released by volcanic eruptions. The range of metabolic strategies was vast, and most of them didn't just work without oxygen, they fundamentally depended on its absence. Respiration, as we know it, hadn't evolved because it couldn't. One does not build a complex oxygen handling system in a world that offers none. And without oxygen in the environment, there was no evolutionary incentive to extract energy from it. Other pathways worked perfectly well, especially for simple, single-celled organisms. There was no pressure to do more. But that was beginning to change, slowly, subtly. Microbes like cyanobacteria were ceaselessly releasing oxygen into their local environments, and some of that oxygen tenaciously clung on in micropockets within microbial mats or in thin water layers near the surface. These regions became miniature oases of oxidation, chemically distinct from the vast anaerobic world surrounding them. They were small, almost imperceptible, but they were persistent. In these unique microenvironments, new evolutionary pressures emerged. Oxygen, paradoxically, could be toxic to organisms that weren't prepared for its reactivity. It damaged proteins, disrupted membranes, and profoundly altered metabolic reactions. Microbes that had evolved in its absence suddenly had to find ways to cope. Some simply avoided it. Others evolved ingenious defenses. A fortunate few discovered ways to actively use it. The step from oxygen tolerance to active oxygen use was gradual, a slow, patient climb. But once it began, the payoff was immense. Aerobic respiration, the process of efficiently extracting energy from organic molecules using oxygen, is far more efficient than anaerobic pathways. It yields significantly more energy per molecule of food, allowing organisms to grow faster, move more, or build more complex structures. But in the Archean, that immense potential was still largely unrealized. The environment wasn't ready. The oxygen wasn't available in high enough concentrations. The chemistry hadn't yet caught up to the possibilities. Even so, faint traces of adaptation were beginning to appear. Some microbes developed specialized enzymes to neutralize reactive oxygen species, those damaging byproducts of accidental oxygen exposure. These protective systems, over immense spans of time, could eventually evolve into sophisticated tools for intentionally utilizing oxygen. But the leap wasn't forced. It wasn't urgent. Oxygen was still scarce. Anaerobic life still ruled. The air itself profoundly reflected that reality. It didn't support combustion. It couldn't sustain a flame. There were no fires, no oxidative weathering, no rust on land. Rocks exposed at the surface were altered by water, not by air. Soils didn't form the way they do today. There were no forests, of course, no lungs breathing in and out. But more than that, there was no air to support breathing in the first place. The absence of oxygen meant the absence of a whole category of processes. No aerobic decomposition, no large-scale ozone layer, no visible signs of respiration. The Earth was active, alive, but profoundly quiet in a way that's almost impossible to imagine now. No wind whistling through leaves, no chirping, no breathing, no sound shaped by air and throat and muscle, just chemical cycling, persistent microbial mats, and a sky-tinted pink or orange depending on the prevailing methane. We tend to perceive breathing as a basic, fundamental function, something elemental to all life. But on the vast scale of Earth's history, it is a late arrival, an adaptation to a profoundly changed world, not a starting point. For most of Earth's existence, respiration was microbial, slow, and anaerobic. Breathing wasn't missing, it simply wasn't needed, and yet the seeds were there. The microbes photosynthesizing in the shallow seas, the mats meticulously building stromatolites, the occasional oxidative burst in small, isolated pockets of water. All of it was preparation, quiet, cumulative, and eventually irreversible. The immense sinks that absorbed oxygen were slowly, inexorably filling up. The sources that produced it were growing, and the delicate balance was beginning to shift. No one would have noticed. There were no lungs to inhale the change, no minds to perceive it, but the chemistry was moving. The Earth was heading towards something profoundly unfamiliar. Not because of a singular event, but because of a threshold, one that once crossed could not be undone. Breathing wasn't invented yet, but the world was beginning to construct the very conditions that would one day make it possible. Oxygen was no longer just a byproduct. It was becoming a force, and eventually it would tip the scales, changing the air, changing the ocean, and changing what life could ultimately become. If you had somehow found a way to stand on solid ground during the Archean, beneath a dimmer sun and above greenish seas, you wouldn't have stayed there long. The air would kill you, the radiation would strip your skin, and the intense heat in many places would be unbearable. But even if you could somehow ignore all that, somehow stand there safely, there would be something else that felt subtly strange, without you quite being able to name it. The day would pass too fast, for the Earth spun significantly faster then. A full rotation took only about 14 hours. The reason has nothing to do with the atmosphere or the crust or anything on the surface. It's a matter of fundamental physics deeply baked into how the Earth formed and how it has changed since. After the planet's violent beginning, and especially after the colossal giant impact that formed the Moon, the Earth was left spinning rapidly. That immense momentum persisted over billions of years. It has been slowing down, but only gradually. The intricate mechanism behind that slowdown is the Moon itself. The gravitational interaction between Earth and Moon causes tidal friction, a subtle but constant drag as the ocean bulges attempt to align with the Moon's pull, but lag slightly behind due to Earth's rotation. That drag ceaselessly transfers angular momentum from the Earth to the Moon, pushing the Moon slightly farther away while gradually slowing Earth's spin. The result? Longer days. But during the Archean, this profound process was still in its early, more fervent stages. The Moon was much closer, perhaps only about 200,000 kilometers away, less than two-thirds its current distance, and the tides it caused were far more extreme. Ocean bulges were larger, coastal zones experienced stronger, more dramatic shifts in water level, and the Earth itself rotated much more quickly, completing a full spin in under two-thirds the time it does today. This shorter day had profound consequences, not just in terms of sunlight hours, but in how energy cycled through the environment. Faster rotation meant stronger Coriolis effects, which profoundly influence wind and ocean currents. It meant shorter exposure times to the sun for any given location, which could impact surface heating patterns and indirectly climate dynamics. And for early life, especially photosynthetic microbes, it meant that light and dark cycles were fundamentally different than what they are now. The microbial mats growing in shallow seas had to adapt to this rapid rhythm. Daylight hours came and went quickly. The precious window for photosynthesis was narrower. Night came sooner. That shift affected metabolic cycles, growth rates, and the very structure of microbial communities. Some organisms may have evolved to maximize energy capture in short, intense bursts. Others might have leaned on internal rhythms, primitive circadian mechanisms, to anticipate light and dark and prepare accordingly. It's unclear exactly how tightly early microbes were tied to the daylight cycle, but it's reasonable to assume the rhythm profoundly mattered. Photosynthesis, for example, is sensitive to light availability. Growth rates change depending on the delicate balance of energy production and storage. A 14-hour day would fundamentally affect how organisms manage those intricate processes, especially in environments where competition was fierce and resources were scarce. The shorter day also implied more days per year. Earth's orbital period, the time it takes to complete one revolution around the Sun, hasn't changed significantly, but with shorter rotations, there were more rotations within a single orbit. That means more sunrises, more sunsets, and more tidal cycles in a given year. The frequency of tides, in particular, would have been striking. Some coastlines might have experienced multiple significant tides per day, each stronger and more dramatic than those we observe now, due to the moon's proximity. That immense tidal energy also exerted profound geological effects. Its ceaseless stirred shallow seas drove sediment redistribution and meticulously shaped coastal microenvironments. In these dynamic zones, where water levels rose and fell dramatically and regularly, microbial mats would have encountered both immense intention and formidable challenge. Tides could briefly expose mats to the air, such as it was, triggering chemical changes. They could also erode and reshape habitats, forcing communities to rebuild. But that disruption also moved vital nutrients, oxygenated shallow water layers, and opened new surfaces for colonization. The stronger tides and faster planetary spin may also have contributed to more vigorous ocean mixing. In an Archean world where the surface ocean was chemically distinct from the deep, vertical mixing was crucial. It helped cycle vital nutrients. It allowed nascent oxygen from photosynthesis to penetrate slightly deeper. It distributed iron, sulfur, and other compounds in ways that profoundly affected microbial metabolism. A fast-rotating Earth wasn't just spinning quickly, it was subtly, but constantly, churning itself. For the planet as a whole, faster rotation implied more intense weather systems. Wind patterns were shaped differently. Storms, if they existed in recognizable forms, would have behaved in unfamiliar ways. Atmospheric circulation, though still primitive in its modern structure, responded keenly to the Coriolis effect, which intensifies with shorter days. That means cells of rising and falling air, the large-scale conveyor belts of planetary climate, may have been narrower and fast. Even the very shape of Earth itself was subtly different. Faster spin created more centrifugal force, which caused the planet to bulge more significantly at the equator. That equatorial bulge would affect ocean depth distribution, gravitational pull, and even how water moved across the surface. None of these differences were enormous on a human scale, but they accumulated over billions of years. They shaped how continents formed, how seas behaved, and how life adapted. And all of this was unfolding silently. In a world without clocks or calendars, time moved at its own pace, set by physics, slowed gradually by the moon. Life adjusted. It had no choice. The fundamental rhythms of Earth were not optional. They were the background conditions that shaped what could evolve and how it would survive. The most striking part of this isn't merely that days were short. It's that they've been lengthening ever since. Every century, Earth's rotation imperceptibly slows by a fraction of a second. The moon continues its slow drift away, a few centimeters per year, and the tides pull at the planet like a gentle, persistent brake. It's barely noticeable on our fleeting timescales, but over billions of years, it fundamentally changes the structure of experience itself. What we now call a day is not fixed. It is a moving target, an evolving rhythm. In the Archean, no conscious entity was watching the sky and meticulously measuring the hours, but time was still passing, and the way it passed, quickly, with more cycles per orbit, more tides per day, and more sunrises per year, left its indelible imprint, not in clocks, but in sediments, in ripple marks on ancient shores, in layered stromatolites responding to light, in the wear patterns of rock shaped by water that rose and fell in regular, tireless rhythm. The Earth was rotating fast, moving forward, gently dragging everything along with it. Microbes, minerals, oceans and atmosphere, and all of it was bound together by motion, not just in space, but in time, a time that was not yet counted in 24 hours, a time that spun by faster, but still slow enough to meticulously shape a world. The early Earth didn't seem to have much going for it, at least in terms of inherent protection. No ozone layer, no thick forests to filter sunlight, no atmosphere safe to breathe. But beneath all that, below the crust, beyond the surface chaos, something profound was quietly working in its favor, something silent, planetary, and persistent, a magnetic field. This field didn't announce itself. You couldn't see it, you couldn't hear it, but it was there, extending far out into space in invisible arcs, gracefully deflecting charged particles from the sun and the wider galaxy. These particles, solar wind, cosmic rays, high-energy radiation bombard planets indiscriminately. They strip away atmospheres, shred molecules, and transform surfaces into barren wastelands. But Earth possessed a shield. The magnetic field originated from the core. Deep inside the planet, the inner core was likely already solidifying, or at least beginning its slow crystallization. Around it, the outer core remained molten, a vast layer of liquid iron and nickel swirling under immense pressure, moving in grand convective patterns. As this conductive fluid moved, it generated powerful electrical currents. Those currents in turn produced a magnetic field. The process is known as the G dynamo. It is a self-sustaining system. Motion creates current, current creates field, field influences motion, and the result is a planetary magnetic bubble stretching tens of thousands of kilometers into space. This field doesn't completely halt the solar wind, but it diverts most of it, guiding particles around the planet, trapping some in radiation belts, and crucially preventing the constant erosion of Earth's nascent atmosphere. Other planets, like Mars, weren't so fortunate. Mars may once have possessed a magnetic field, but it faded early. Without that enduring protection, the solar wind gradually stripped away its atmosphere. Over time, what remained was thin, cold, and incapable of supporting surface water. Earth, by contrast, held on, not just because it occupied the right orbital spot, but because it kept its core actively churning. In the Archean, this silent protection was absolutely critical. The sun was more active than younger, more volatile, producing frequent solar flares and intense bursts of charged radiation. Earth's atmosphere, still in its formative stages, had little capacity to block high-energy particles on its own. Without a magnetic field, much of the precious water and nascent air might have been irrevocably lost to space, pulled upward and flung away by the relentless assault of the solar wind. The field also played a vital role in preserving the chemical stability of the upper atmosphere. It reduced the stripping of hydrogen, which otherwise might have escaped into space over time, and helped maintain the conditions necessary for surface water to persist. It didn't render the Archean Earth entirely safe, but it made it survivable, a fragile haven in a harsh cosmos. Life, still microscopic and largely confined to the protective oceans, may not have needed to comprehend any of this, but it benefited from it constantly. UV radiation from the sun was still a problem. There was no ozone layer to absorb it, but the most dangerous cosmic particles were largely deflected or absorbed before they reached the lower atmosphere, or surface. That reduction in radiation allowed more stable environments to develop, especially in water. Magnetic fields leave few obvious direct traces in the fossil record, but they do leave tantalizing clues in rocks. Certain minerals, especially iron-bearing ones, align themselves with the magnetic field during their formation. When lava cools or sediments settle, these mineral grains lock into place, preserving the direction and strength of the field at that precise time. Studying these ancient alignments, a field known as paleomagnetism, allows scientists to meticulously track the history of Earth's magnetism. From Archean rocks, we know the field existed. It was weaker than today's, possibly more chaotic, but it was undeniably present, and it was strong enough to deflect solar particles and help retain the atmosphere. This invisible system, born from deep Earth processes, was a quiet, unassuming partner in the survival of early life. It also played a subtle role in navigation, not for animals, not yet, but for charged particles and electric currents in the upper atmosphere. It influenced how auroras formed, where radiation was deposited, and how the ionosphere behaved. These effects are subtle but widespread. They shape atmospheric chemistry, they affect the distribution of energy in the planet's upper layers, and in a time before biology had teeth, eyes, or lungs, they were part of the fundamental operating conditions life had to work with. Some hypotheses even suggest that hydrothermal vents, those possible cradles of life, might be influenced by local magnetic variations, either through rock magnetism or electrical conductivity in the surrounding environment. It's speculative, but it underscores the profound idea that magnetism wasn't just a planetary defense. It may have shaped habitability in ways we still don't fully understand. Over time, the magnetic field would fluctuate. It would reverse polarity, strengthen and weaken, shift its configuration, but it never stopped. As long as the core stayed active, the shield remained, and as Earth's surface changed, as continents formed, oceans evolved, and life became more complex, the magnetic field stayed steadfastly in place, always silent, always working. Today, we depend on it without thinking. It protects satellites, it guides migratory animals, it defines space weather, and it still guards our atmosphere from solar stripping. But its roots extend all the way back to a time when Earth's interior was hotter, its crust thinner, and its surface chemistry raw. In that primordial world, life had almost no defenses, except this one, a planetary field generated from below, reaching out into space and holding back the worst of what the universe had to offer. It's almost impossible to truly imagine Earth without life, not because we can't picture it visually, but because we cannot fathom the profound silence. Not the kind you find in a quiet forest or a still morning, but something far deeper, a kind of silence that has never heard wind rustling through leaves or the gentle whisper of grass or the chirp of a single living thing. During the Archean, the land was lifeless in every visible way. There were no plants, no insects, no animals. No roots held the nascent soil. Without plants, there were no forests, no undergrowth, no meadows. Without moss or fungi or lichens, all of which would come much, much later, there were no pioneer species clinging to rock, no slow work of organic transformation. The continents, or the few large land masses that existed, were utterly bare. Their surfaces were jagged, sharp, unstable. Volcanic flows, vast basaltic plains, and slowly forming protocratons dominated the terrain. Occasionally, volcanic activity would break the monotony: explosions, deep rumbles, sudden gas releases. Ash could cloud the sky. Lava could pour into the ocean, boiling it, sending up plumes of steam. But even these dramatic events were followed by silence. No animals fled. No predators took advantage of the disruption. The land simply endured. Even underground, there was no activity in the way we understand it now. No worms aerating soil, no insects burrowing or decomposing organic matter. Earth's crust moved, flexed, cracked, but it did so alone. Life had not yet learned how to live on land. All of biology was still confined to water, and only in some parts of it. The colors of the landscape reflected this profound emptiness. No green, obviously. Mostly greys, blacks, browns. The stark colors of rock and ash, maybe the occasional chemical staining from minerals, reddish iron oxides, yellow sulfur deposits, pale crusts from evaporated salts. but nothing like the saturated palette of modern Earth. No seasonal change, no spring bloom, no autumnal decay. The land didn't change because nothing was living on it to change with the seasons. Sunlight hit the surface without resistance. No canopy filtered it. No shade protected the ground. On days when the sky was clear, UV radiation reached all the way to the rock. On days when volcanic haze or methane-induced smog filled the air, the light dimmed and softened, but even then, nothing stirred in response. The earth turned under the sun, profoundly untouched, and yet life knew this land existed. Microbes didn't live on it. Not yet, but they felt its presence. Rivers carried nutrients down from these rocky slopes. Erosion added minerals to shallow seas. Volcanic activity poured elements into the water that microbes used for metabolism. The land and the ocean weren't separate. They were in constant conversation, even if one side was still silent. Eventually, that silence would end. Microbes would begin to colonize damp surfaces near the waterline. Over long time scales, they would adapt to desiccation, to radiation, to low nutrient environments. They would begin to form crusts, microbial layers that could trap dust, fix nitrogen, and survive in harsh conditions. But in the Archean, those experiments were still ahead. The land remained quiet and still, for all its emptiness. The land was essential. It was the place where continental crust was forming thick, buoyant blocks that resisted subduction. It was where weathering began to draw carbon dioxide out of the atmosphere, slowly shaping the planet's climate. It was where the indelible record of Earth's deep history would be written in layers of volcanic rock, sediments, and minerals altered by water. Even in its profound silence, it was meticulously storing information. Today, it's hard to find a landscape untouched by biology. Even deserts hewn with microbial activity. Even the harshest cliffs host moss or lichen. But the Archean land was untouched in the truest sense. Not pristine, but unclaimed. It had not yet been used as habitat, not yet converted by roots or reshaped by animals. It was raw. The silence of that land was not peaceful. It wasn't the quiet of stillness after motion. It was the quiet of absence, not of noise, but of participation. Nothing breathed there. Nothing died there. Nothing tried to hold on or take shelter. It was Earth, not yet a home, but patiently waiting. And from the perspective of life in the ocean, the land must have seemed distant, irrelevant, maybe even dangerous. But it was part of the same grand system. The same tides that shaped coastlines, fed nutrients into the sea. The same volcanoes that built islands, altered ocean chemistry. The land was part of the loop. Even if no one was there to walk across it or listen to its profound silence, one day that would change. Life would begin to climb out, to touch rock, to survive sunlight, to breathe air. But for now, the land stood still, unburdened by life, unbroken by roots, and above it, a sky with no birds. Below it, a world building slowly towards something more. The Archean Earth was hot, but not in the way we usually understand it. It wasn't dotted with dancing flames, and it didn't blaze with open fire, because fire, in the conventional sense, didn't really exist yet. Fire as we know it needs oxygen. Combustion is a profound reaction. Fuel meets air, and heat does the rest. But the Archean had no air to burn. Oxygen hadn't accumulated. The raw materials were there. Carbon-based matter, volcanic gases, heat everywhere. But the spark couldn't quite catch. Not until the fundamental chemistry of the planet slowly, inexorably changed. So instead of flames, the heat came from below, from the planet's churning interior, still bleeding off the immense energy of its violent formation. Heat from relentless radioactive decay, from residual energy trapped in the Thur, from constant tectonic motion. That heat moved upward through the mantle, reaching the surface in dramatic eruptions and effusive flows, in steaming fissures and vast molten plains. Lava poured, not with sudden explosive bursts like modern volcanoes, but sometimes in sheets, slow, wide, basaltic flows that covered immense landscapes and meticulously built new ground. There were places on the Archean Earth where rock barely had time to solidify before being buried again in another layer of lava. The crust was thinner then, more flexible, more prone to cracking. Heat moved through it more directly. Volcanic islands emerged and vanished. Ocean ridges split open and oozed molten rock into the sea. Even areas not actively erupting were intensely hot beneath the surface. Geothermal gradients were steeper. The land, if you could call it that, often steamed without a flame. This constant geothermal activity made the Earth feel alive in a purely mechanical way. Not organic, but dynamically restless. Heat fundamentally changed water chemistry. It built vast hydrothermal systems that powered nascent microbial metabolism. It fractured rock and fed vital minerals into the sea. It created isolated pockets where life could hide from damaging UV radiation and discover vital nutrients and chemical gradients. Life, such as it was, didn't just survive heat. It profoundly needed it. But heat wasn't everywhere, and its absence didn't necessarily mean calm. Just as fire couldn't exist without oxygen, ice couldn't form easily either. Not in the same dramatic, glacial ways we observe now. There's fascinating debate over precisely how cold the Archean Earth became. Some models suggest the planet remained largely warm thanks to potent greenhouse gases, like methane and carbon dioxide, which efficiently trapped heat from the dimmer young sun. Others propose that temporary cooling events did occur, that clouds of volcanic ash or shifts in carbon cycling may have led to brief cold periods, perhaps even early glaciation in isolated regions. But even if ice formed, it did so without the usual visual cues. There were no snowy mountaintops, no immense polar caps stretching across continents, no vast ice sheets grinding valleys into the crust. The land was too raw, the atmosphere too thin, the ocean chemistry too different. If ice came, it came quietly. It didn't reshape the world the way glaciers eventually would in later eons. The cold, when it happened, didn't need snow to be dangerous. A dip in temperature could profoundly alter ocean circulation, affect the solubility of gases, change the chemistry of shallow basins where microbial life was most active. Cold could slow photosynthesis, it could make nutrient cycling less efficient. Even small shifts had big consequences, not because life was inherently fragile, but because it was simple, with few backups and no complex ecosystems. A failed microbe community might mean nothing recolonized the area for centuries. Still, the dominant climate leaned warm. The sun, in its early days, emitted less light than it does now, roughly 70 to 75% of today's output. By all accounts, that should have left the Earth frozen, a desolate ice ball. But it didn't. Greenhouse gases made up the crucial difference. Methane, in particular, was abundant, produced by early microbes and volcanic activity alike. Methane traps heat incredibly efficiently, more so than carbon dioxide, and in the profound absence of oxygen, it could build up to levels that would be acutely toxic today. This powerful greenhouse effect kept the oceans liquid, the atmosphere active, and the surface temperature just enough for water to flow, not freeze. But the balance was delicate. Too many volcanic eruptions, too much weathering, or even subtle biological shifts could tip the scales. Earth's temperature wasn't locked in, it drifted cool, not seasonally, not even on human timescales, but on immense geological ones, millions of years up, millions of years down. Local conditions varied wildly. Shallow seas, warmed by sunlight and geothermal activity, could be near boiling in places. Deeper waters cut off from circulation might be cold, dense, and stagnant. Hydrothermal vents created isolated environments, with temperatures ranging from freezing just a few meters away to hundreds of degrees near the vent mouth. And on land, bare rock baked under a hazy sun during the day and radiated its heat away quickly at night, with nothing, no vegetation, no insulating soil to moderate the profound swing. There were no forests to hold moisture, no clouds shaped by transpiration, no living ground cover to soften the extremes. Rain, when it fell, hit bare stone or volcanic ash. It pooled in uneven basins. It carved gullies and ran off quickly, unimpeded. Water evaporated fast in some areas, froze in thin crusts in others, and the atmosphere, with its complex mix of methane, CO2, and other gases, carried heat unevenly. Some areas scorched, others cooled too fast. There was no global thermostat, no planetary comfort zone, and yet life endured, because these extremes, this heat without fire, this cold without ice, were not chaos. They were the fundamental environmental conditions life was born into. Microbes didn't expect comfort. They didn't wait for stability. They used what was profoundly there. They built communities around hydrothermal systems, adapted to intense UV exposure, evolved metabolisms suited to high temperatures or chemical gradients that only existed in narrow ranges. To us, the Archean might appear uninhabitable. No green, no blue sky, no oxygen, and no comforting warmth. But to the life that evolved in it, it was all there was. Heat came from within the earth, not from combustion. Cold came from a dim sun and a still-forming atmosphere, not from snow. The extremes weren't extremes to them. They were normal. And within those conditions, Earth's long experiment continued. With every lava flow, every volcanic winter, every fluctuation in methane or solar output, life adjusted, not dramatically, not quickly, but with time, because while Earth didn't yet have fire or frost, it had energy, it had water, and it had the profound potential not just for change, but for persistence. In that sense, the Archean climate wasn't hostile, it was profoundly formative. It shaped what life could become by limiting what it could do. And as the crust cooled, as the days lengthened, as the chemistry of air and ocean began to drift towards something more familiar, that early life was ready to follow, molded not by comfort, but by extreme. The moon didn't hang quietly in the Archean sky the way it does today. It wasn't a distant companion casting gentle light across calm oceans. It was nearer, much nearer, nearly twice as large in the sky, and more than twice as powerful in its gravitational influence. It was still moving away bit by bit. But during the Archean, it was close enough to stir the seas like a giant cosmic spoon, and its presence profoundly mattered. The moon had already been around for a while by the time the Archean began. Its origin was violent, a colossal planetary collision with a Mars-sized body named Theia, an impact that tore apart Earth's early crust and threw molten debris into orbit. That debris coalesced into the moon, and the Earth-Moon system settled into a shared gravitational rhythm. But it was a rhythm that began with chaos. Energy had to dissipate. Orbits had to stabilize, and the profound effects lingered. In those early days, the moon was not just a visual feature, it was a powerful force. Its gravity pulled at the Earth, deforming the planet's crust, creating tides, not just in water, but in solid rock. The tidal bulges shifted slowly across the surface as Earth rotated, creating friction, and that friction mattered. It converted kinetic energy into heat. It slowed Earth's spin. It pushed the moon outward. The same dance continues today, but back then everything moved faster and hit harder. Because the moon was closer, its tidal pull was significantly stronger. Estimates suggest the Archean ocean tides may have been 10 times greater than they are now. That implies coastlines changed dramatically, multiple times a day. Water surged inland, retreated quickly, exposed microbial mats, then drowned them again. These shifts weren't subtle. They were sculpting tools. They carved shorelines. They distributed sediment. They created zones of chemical mixing that allowed nutrients to concentrate in places shallow enough for photosynthetic microbes to utilize them. For early life, this mattered more than sunlight alone. The tides created a vital predictability in a world with very little of it. They regulated access to light and nutrients. They exposed surfaces to the air, such as it was, and then submerged them again in seawater. This rhythmic disturbance became a kind of clock, a planetary schedule, and life, still microscopic, still struggling to establish itself, responded. Mats grew in patterns that matched the tides. Colonies adapted to survive brief exposure. Chemical reactions accelerated during transitions between wet and dry. Without the moon, that powerful rhythm wouldn't have existed. The sun creates tides too, but they are weaker, and their influence doesn't produce the same high-frequency shift. The moon's gravity made the Archean world dynamic in a way that static chemistry could never match. It stirred, it pulled, it drove circulation in shallow basins, and may have influenced early ocean mixing on a global scale. and it profoundly shaped the length of the day. As Earth's rotation slowed due to tidal friction, the day lengthened from a frenetic 6 hours after the moon's formation to about 14 hours during the Archean to the 24 hours we live with now. This change was gradual but relentless. It altered everything from wind patterns to energy distribution, and again it was the moon doing the work. The moon's position in the sky was not constant. It rose and set, shifted through its phases, but because it was so much closer, it would have appeared enormous, filling a large portion of the horizon, glowing not with firelight, but with the cold, ancient reflection of a young sun. There were no eyes to see it, no organisms on land to watch it rise, but it was there, every day and night, tugging invisibly at water, stone, and time itself. We don't know exactly how much of the moon's surface was geologically active during the Archean, but its impact on Earth was undeniably clear. The tides helped stabilize the planet's tilt, a major factor in long-term climate stability. Without the moon, Earth's axial tilt could wobble dramatically over millions of years, swinging from near zero to chaotic extremes. With the moon, the tilt stays within a narrow, predictable range, keeping seasons relatively consistent and helping maintain temperature gradients that support ocean circulation. And while the moon doesn't produce light of its own, its phases would have created a secondary rhythm in the Archean world, a slow pulse of bright and dim nights, full moons and new moons, reflected across the vast oceans. For microbial life in the sea surface, this periodic change in light might have been detectable. For life in tidal zones, the alignment of lunar and solar tides created especially extreme shifts, spring tides that reached farther inland or withdrew more dramatically. Eventually, the moon would become a distant reference point, a cosmic timekeeper, a symbol, an anchor for calendars and stories. But in the Archean it had no mythology. It was just gravity, just motion. And yet its influence was profound. It helped regulate Earth's rotation, stabilize its climate, drive its ocean dynamics, and give early life something close to a rhythm. Today we rarely contemplate that ancient influence. The tides seem passive, the moon feels distant, but it is still moving away, about 3.8 centimeters per year, and Earth is still slowing down. In time, days will lengthen further, the moon will orbit farther, and yet its ancient role remains etched in rock, in banded sediments shaped by tidal currents, in the fossils of stromatolites that grew in tune with the sea, in the chemical layers that record wet and dry cycles across billions of years. Back in the Archean, the moon wasn't just in the sky, it was in the water, in the rock, in the very spin of the planet itself. It didn't speak, but it moved, and the Earth, from its crust to its tides to the earliest living cells drifting in shallow seas, it was there, leaking out in small, imperceptible amounts. Long before it could do anything noticeably, oxygen made by diligent microbes, quietly harvesting sunlight, patiently splitting water, and discarding a waste product that no one yet needed. In the early oceans, cyanobacteria had already figured it out. Oxygenic photosynthesis, an ingenious way to use water and carbon dioxide to build sugars and release vital energy. And with it, they released oxygen into the world. But the world had no place for it yet. The story of oxygen on Earth is not one of immediate dramatic transformation. It's a story of waiting, of slow, patient accumulation, of profound resistance, of everything in the environment trying its utmost to neutralize, absorb and bury oxygen before it could ever build up. And for a very long time, hundreds of millions of years, the environment successfully resisted. In the Archean oceans, oxygen was instantly consumed by iron. Dissolved iron, abundant in the anoxic seawater, reacted voraciously with the nascent free oxygen, forming insoluble ferric compounds that sank and collected on the seafloor. This powerful reaction built the layered rock structures we now call banded iron formations, deep red and grey stripes that mark ancient rhythmic episodes of oxygen release and removal. These formations appear across the Archean timeline, quiet, enduring evidence of a planet absorbing as much oxygen as it possibly could, as fast as it could. The oxygen produced by photosynthesizers also reacted with ubiquitous sulfides, methane, and other reduced compounds in the ocean and atmosphere. These reactions rapidly stripped oxygen out of circulation. They stopped it from accumulating in the air. The oceans were the first grand battleground, a chemical war between production and removal, and life itself was paradoxically generating both sides of the fight. Cyanobacteria created oxygen. Other microbes consumed it or created compounds that neutralized it. The balance was always in motion, always delicate. It wasn't just a matter of sheer quantity. It was about profound thresholds. Oxygen had to reach a certain critical level before it could begin to persistently exist, before the immense sinks became saturated and the surplus started to truly linger. Until then, every oxygen molecule was essentially erased, its existence fleeting. And yet, the microbes kept making it. Not for us, not for the distant future, just because it worked for them. Oxygen was a byproduct, not a goal. For the microbes performing photosynthesis, it was the waste product they had to release to keep growing. And that growth was relentlessly driven by energy. Light streamed in from above, filtered through haze and cloud, and in the right places, shallow seas, tidal flats, protected lagoons. It was enough. Microbial mats layered themselves across surfaces. They photosynthesized during the day. They processed nutrients at night. They meticulously built domes. They spread. And all the while, they kept leaking oxygen into a world that wasn't ready for it. Some of that oxygen tenaciously clung on in microenvironments, tiny, isolated zones within mats where chemistry had subtly shifted. Thin surface layers of water where light penetrated and oxygen hovered just long enough to matter. These were islands of nascent habitability in an otherwise hostile sea, and in those islands, biology slowly began to adapt. Some organisms developed ingenious ways to detoxify oxygen. Others began to exploit it, but they were still outliers, living in bubbles of chemistry, surrounded by a vast, anoxic world. Meanwhile, oxygen's slow, quiet assault on the planet continued. It gradually changed mineral structures. It altered weathering rates on land. It affected the solubility of metals in the ocean. Each small, subtle change fed back into the intricate system. Some changes encouraged more oxygen production. Others limited it. The whole planet was involved, not passively, but chemically in resisting and eventually enabling the rise of this reactive gas. The long wait for oxygen is sometimes referred to as the oxygen lag, the immense period between the evolution of oxygenic photosynthesis and the moment when oxygen began to truly accumulate in the atmosphere. That lag lasted for more than 1 billion years. For perspective, that's longer than all multicellular life has existed. It's longer than the entire time since the first animals appeared. It's an immense stretch of geological patience. And during that time, life was still experimenting, still spreading, still inventing ingenious new ways to survive. The profound absence of oxygen didn't halt evolution, it simply shaped its direction. Anaerobic metabolisms remained dominant. Chemosynthetic communities near hydrothermal vents flourished. Microbes used sulfur, nitrogen, hydrogen, anything but oxygen, to power their survival. In some cases, the appearance of oxygen created immense stress. It killed off organisms that couldn't adapt. It forced life into new, more marginal niches, away from the poison zones. There may have been brief moments, regional events, short-lived increases when oxygen levels rose above the usual baseline, enough to affect chemistry, but not enough to change the world. These were false starts, fleeting spikes, episodes that left traces in rock, but didn't lead to lasting transformation. The system pushed back. The sinks were still too strong. The balance still tilted against accumulation. But something was shifting slowly and inexorably. The oxygen sinks were filling up. Iron concentrations in the ocean dropped. More banded iron formations formed, then gradually declined. Methane levels, once stabilized by a haze-producing atmosphere, began to fall. Oxygen's influence crept outward, becoming harder to isolate, to microenvironments. The stage was meticulously setting for a permanent, global change. That profound change wouldn't happen until well after the Archean, during the Paleoproterozoic, in what's known as the Great Oxidation Event. But the groundwork was all here. The microbes, the mats, the endless sunlight, the quiet, tireless leak of oxygen into a world not designed to handle it. And over time, that leak became a trickle. a trickle, a flow. Eventually, the chemistry would break. The threshold would be crossed. What followed that crossing was not an immediate explosion, but a long drawn-out transformation. Oxygen rose gradually, then in bursts, then settled into new equilibriums. The atmosphere changed. The biosphere reorganized. Entire groups of microbes disappeared, unable to survive in the new oxidizing world. Others took their place. Complexity became possible, but in the Archean, that was all in the future. The weight was still on, and the world, strange and breathingless, went about its business. Volcanoes erupted, continents shifted, tides rose and fell. Life carried on, mostly unaware that it was reshaping the atmosphere, one molecule at a time. The long wait for oxygen was not a pause. It was a process, one that moved quietly in sunlight and sediment, in layers of microbial film, in the intricate chemistry of seawater and the very crust of the planet itself. And when it finally tipped, the world would never be the same again. It's a fair question, one that might linger as you drift into deeper contemplation. If you stand on a beach or hike a mountain trail today, you are surrounded by things you can see and touch: trees, rocks, animals, clouds. But the Archean, that's so far back. It's not just before people, it's before bones, before leaves, before shells, before the very things that usually fossilize and fill museum drawers. So how do we know what Earth was truly like back then? What the atmosphere held, what the oceans were made of, what the land looked like, and what minuscule microbes were doing in the shallow waters? We know because the Earth remembers, even if it doesn't remember with perfect clarity. It keeps meticulous records in rock. Not photographs, not detailed narratives, just physical and chemical patterns left behind by ancient processes. And if you know how to patiently read those patterns, you can meticulously reconstruct the world as it once was, not with absolute certainty, but with enough compelling clues to piece together a coherent, if hazy, picture. The oldest pieces of the planet we still possess are rock. Some of them are over 4 billion years old, especially a remarkably durable mineral called zircon. Zircon forms in molten environments and can miraculously survive even when the rest of the rock has been destroyed. Zircons contain uranium, which decays into lead at a known precise rate. By measuring how much lead has formed inside a zircon grain, scientists can determine its age, sometimes down to a window of a few million years, which is astonishingly precise when you're dealing with events more than 3 billion years ago. Some zircons are found inside younger rocks, which tells us not just how old the grains are, but what kind of environment they formed in. Their chemical composition contains subtle hints of the water they crystallized in. Oxygen isotopes, for example, suggest liquid water existed on the surface of the planet as early as 4.3 billion years ago, even before the Archean began. Other rocks, especially the majestic banded iron formations, meticulously record the activity of oxygen in the ancient ocean. These are sedimentary structures made of alternating layers of iron-rich minerals and silica. They only form under very specific chemical conditions: abundant dissolved iron in the ocean and periodic exposure to oxygen. The oxygen would cause the iron to oxidize and fall out of solution, layering onto the seafloor. Then, when oxygen levels dropped again, the silica could settle, layer after layer, this pattern repeated for eons. And when we find banded iron formations in Archean rock, we are looking at the very pulse of oxygen production and removal, written directly into the seafloor itself. There are also isotopic fingerprints in ancient carbon. Life tends to prefer the lighter version of carbon, carbon-12 over the heavier carbon-13. When ancient microbes photosynthesized or metabolized carbon-based molecules, they left behind material enriched in carbon-12. These subtle traces, miraculously preserved in sediment, suggest biological activity even in the profound absence of body fossils. When we analyze the carbon isotope ratios in rocks dated to more than 3.5 billion years ago, we find tantalizing hints of life. Not life we can see, but life that left an indelible chemical shadow. Sulfur isotopes also tell a compelling story. In the Archean, the atmosphere had little to no oxygen, and the way sulfur cycled through air and water was profoundly different. Volcanic gases released sulfur compounds into the atmosphere, and without oxygen, they underwent unusual reactions driven by ultraviolet light. These reactions left behind distinct isotope ratios called mass-independent fractionation that only occur in an anoxic atmosphere. We find these unique signatures in Archean rocks, and when they disappear from the record, it marks a profound shift, the undeniable rise of oxygen, a planetary chemical transition visible only at the molecular level. In places like the Pilbara Craton in Australia or the Barberton Greenstone Belt in South Africa, we find well-preserved ancient sediments folded, buried, and metamorphosed, but still containing the basic structures of Earth's early surface. In some of these rocks, we even find stromatolites, those fossilized microbial mats that meticulously built themselves up in layers over time. These aren't fossils of the microbes themselves, but they're fossils of what the microbes built, dome-like structures laminated with growth rings, showing that life was actively shaping its environment in a structured, organized way. Even the absence of certain features tells us something profound. There are no animal fossils in Archean rocks, no plant impressions, no signs of oxygen-dependent minerals forming at the surface. That absence isn't a blank, it's a crucial data point. It tells us what the Earth couldn't yet support. We also look at detrital minerals, grains of stable minerals like uraninite or pyrite, that in today's oxygen-rich world would oxidize and disappear before they could be buried. In Archean sediments, these minerals miraculously survive transport through rivers and streams because the atmosphere wasn't yet oxidizing. Their presence is a strong, silent indicator that the air was low in oxygen at the time they were deposited. None of this is easy to read. These rocks are ancient, altered, fractured, and sometimes folded beyond recognition. The isotopic signatures can be subtle, the structures ambiguous. It takes patient comparison, rigorous cross-checking, and often passionate disagreement among scientists to build a coherent picture. And yet, over decades of dedicated work, that picture has slowly, painstakingly come into focus. We don't see the Archean directly. We see it refracted through the intricate evidence it left behind, in mineral grains that remember their formation, in chemical ratios that preserve biological bias, in structures shaped not by organisms themselves, but by their persistent behavior, in sediments that still bear the subtle influence of tides pulled by a closer moon. And that's how we know, not from stories, but from the physical consequences of what happened. The Earth, even at its most hostile and unrecognizable, still obeyed the fundamental rules of physics and chemistry, and it left behind a profound record. As long as you know how to look, it's not perfect. There are gaps. Whole continents have been subducted, cretons shattered, records erased. The Archean is a partial archive, one that must be interpreted carefully, always with a margin of uncertainty. But it's enough to tell a story, not in full color, not in sharp detail, but clearly enough that we can say, this is what it was probably like. This is what life was doing. This is how the world began to become its. And in that story, we find ourselves not directly but distantly, because everything we are came from that quiet, deep, ancient world, the one with no breath, no trees, no fire, no sound, just rock, water, light, time, and the first stubborn signs of life, writing its story, molecule by molecule, into the only surface it had. By the time the Archean Eon gracefully gave way to the next, the Earth hadn't transformed all at once. There was no sudden shift in color, no sharp line drawn across the crust. The ancient rocks didn't notice. The tireless microbes didn't hold their breath. The planet kept turning, just a little slower than before. The sun kept rising over oceans that still held no fish, and the air, still mostly unbreathable, had just the faintest, most hopeful trace of something new within it. This is how change truly unfolds on a planetary scale. Quietly, gradually, with immense periods of almost imperceptible stillness, followed by brief, potent pulses that never fully allow things to revert to how they once were. The Archean didn't conclude because it was over. It concluded because the very conditions that defined it, the chemistry, the heat, the crust, the atmosphere, the pace of its cosmic dance, slowly, inexorably shifted until they became something else entirely. Oxygen had begun its tentative accumulation in places it couldn't before. The photosynthesizers were still working, diligently as ever, but the vast oxygen sinks were weakening. Iron was harder to find. Sulfur was changing its chemical dance. The ocean and atmosphere were no longer able to hold oxygen down completely, and that single profound change would eventually unlock everything that followed. The continents, once just scattered fragments of nascent crust, had started their slow, patient journey of coming together, not forming full supercontinents, not yet, but assembling pieces of buoyant landmass that stubbornly persisted. They moved slowly, collided, deformed, mountains majestically rose, patiently weathered, and eroded into rivers that carried precious minerals back into the sea. The cycle of rock had deepened. So too had the cycle of life, and life, still microscopic, still largely invisible, was beginning to alter its surroundings in ways that left clearer, more lasting traces, not just in the deep reds of banded iron or the subtle shifts of carbon isotopes, but in layers of organic material building up faster than ever before. Life was no longer merely adapting to the Earth, it was profoundly shaping it. Even the sky was subtly different now. The pervasive haze that once filled it, largely driven by methane and the profound lack of oxygen, was thinning. Blue was starting to appear faintly on certain days, in certain places, not often, not everywhere, but enough to hint at a new dawn. The sun, still dimmer than today's, was steady. The moon was slightly farther away, the tides a little calmer, the planetary rotation a bit slower, the same fundamental forces still working, still patiently softening the raw edges of a world that once knew only extremes. And through it all, the Earth kept remembering, layering its stories into rock, holding immense heat in its core, tracing the intricate patterns of life in stone. It didn't know it was writing history, but when we speak of the Archean, we are not speaking of something utterly gone. We are speaking of the part of Earth that still lives within the deepest rocks, in the enduring minerals that form the very base of continents, in the profound legacy of microbes that still perform photosynthesis every single day, in the oxygen we breathe, in the gentle tilt of the Earth, stabilized by the moon that came from the impact before the Archean even began. We carry its history in our very cells and in our sky. The Archean never truly said goodbye. It simply became the Proterozoic, a new eon, with a new atmosphere, a new pace, and eventually new, more complex forms of life. But even then, the foundation remained the same. The continents were Archean at their very core. The first steps toward complexity were built on Archean rules. The Earth was no longer young, but it wasn't old yet either. It was learning how to host life, not just tolerate it, but profoundly support it. And perhaps that's the most beautiful way to describe what the Archean truly was. The immense time when Earth patiently, painstakingly figured itself out. Not in any conscious way, not in a rush, but in long, slow, deliberate processes that meticulously built towards everything else. Fire would come later. So would breathing. So would towering trees and intricate fossils and animals with discerning eyes. But none of that could ever happen until this foundational part was finished. And now it is. So, if you've listened this far, whether lying peacefully in bed, gazing out at the stars, or gently drifting into sleep, thank you for slowing down, for being curious, for letting this story unfold the way the Earth did, steadily, patiently, and without the need for a definitive ending. The Archean didn't have one. It just kept going, perpetually transforming. And so will we. Good night, Archean. Good night, Earth.